Time is something we all experience every day, yet its nature remains deeply mysterious. Among the many ideas that challenge our understanding of time, time dilation stands out as one of the most intriguing. This phenomenon, predicted by the theory of relativity, shows that time does not pass at the same rate for everyone. It is not just a theoretical concept but a real effect that has been observed and measured. Understanding time dilation is important because it changes how we perceive reality, impacts technology, and influences scientific thought. Imagine traveling near the speed of light or being near a massive object. Time for you would pass differently than for someone far away. This is not science fiction but a scientific reality that reshapes our understanding of the universe. At its core, time dilation refers to the difference in elapsed time as measured by observers in different frames of reference. In simpler terms, it means that a clock moving relative to you or situated in a strong gravitational field ticks differently than your own clock. The principle comes from Albert Einstein's theory of relativity, which shows that time is not absolute. The faster you move or the stronger the gravity you experience, the slower your clock ticks compared to someone in a different situation. A common misconception is that time itself changes for everyone in the universe. In reality, time dilation is relative, and each observer measures time differently depending on their motion and position in a gravitational field. People often imagine that time dilation is extreme only in science fiction scenarios, but even small effects occur in everyday life, such as in satellites orbiting Earth, and must be corrected for accurate operation. The concept of time dilation has a rich history. Its origin traces back to the early 20th century, during a period of intense scientific discovery. Albert Einstein introduced the special theory of relativity in 1905, which first suggested that the passage of time depends on motion. Later, in 1915, his general theory of relativity extended this idea to include the effects of gravity. Several scientists contributed to the development of these ideas. Hendrik Lorentz and Henri Poincaré explored transformations related to motion and the speed of light before Einstein, while experimental physicists like Haffel and Keating in the 20th century tested the predictions using precise atomic clocks. The timeline of development shows a combination of theoretical insight and experimental verification, moving from abstract equations to real-world observation. The theory has survived more than a century of scrutiny, proving its robustness and practical significance. Time dilation operates through specific mechanisms governed by the laws of relativity. In the special theory, it occurs because the speed of light is constant for all observers. This constancy leads to the result that a moving clock runs slower relative to a stationary observer. The fundamental equation is simple in appearance yet profound in meaning. If an object moves at velocity v relative to an observer, the time experienced by the moving object is multiplied by the factor square root of 1 minus v squared divided by c squared, where c represents the speed of light. In the presence of gravity, general relativity shows that time is influenced by the curvature of spacetime. Clocks closer to massive objects run slower than those farther away. Both mechanisms reflect the principle that time is not separate from space but part of a four-dimensional fabric that interacts with motion and mass. In everyday life, time dilation can be subtle but measurable. For example, astronauts aboard the International Space Station experience a small time dilation because they travel at high speeds relative to Earth. Their clocks run slightly slower than those on the surface, and over months, the difference becomes detectable. Another observable effect occurs in GPS satellites, which must account for both velocity-based and gravitational time dilation to provide accurate positioning. Without these corrections, the system would quickly become inaccurate by several kilometers. Experiments using atomic clocks on airplanes or high-speed jets also confirm that time passes differently for moving observers. Even though the effect is usually small in daily experiences, these examples show that time dilation is a real and measurable phenomenon that affects technology and navigation. The implications of time dilation extend beyond curiosity. Technologically, it ensures that systems like GPS operate correctly, maintaining global communication and navigation. Scientifically, it deepens our understanding of the universe, revealing that time is not an absolute backdrop but a flexible dimension. The realization that time can stretch or contract depending on motion or gravity has influenced fields ranging from particle physics to cosmology. It also impacts philosophical thinking, challenging ideas about free will, causality, and the nature of reality. Time dilation teaches us that the universe is more interconnected and dynamic than our everyday experience suggests. By applying these principles, scientists and engineers can develop technologies that operate reliably in extreme conditions, from satellites orbiting Earth to spacecraft traveling near the speed of light. Modern research continues to explore time dilation and its consequences. Studies using highly accurate atomic clocks in laboratories and in space test the limits of Einstein's predictions. Experiments with particles moving close to the speed of light confirm time dilation at extreme velocities. Some research investigates how time dilation interacts with quantum mechanics, seeking to unify different aspects of physics. Debates continue about the interpretation of these effects, especially in relation to black holes and the early universe. Future directions include deeper exploration of gravitational time dilation near massive objects and its potential impact on interstellar travel. As our ability to measure time becomes more precise, we may uncover subtle effects that challenge current understanding and open new avenues for technology and theory. Time dilation also presents conceptual challenges and paradoxes. One well-known puzzle is the twin paradox. If one twin travels at near light speed and returns while the other stays on Earth, the traveling twin will be younger. This result seems counterintuitive but follows directly from the equations of relativity. It forces us to reconsider what it means to age and how we experience time. Other paradoxes arise in extreme gravitational environments, such as near black holes, where time can slow dramatically relative to distant observers. Open questions remain about how time dilation interacts with quantum phenomena or whether it could be harnessed for practical applications like future space travel. These challenges show that while the concept is scientifically established, its deeper philosophical implications continue to intrigue thinkers and researchers. In conclusion, time dilation is a profound insight into the nature of the universe. It demonstrates that time is not fixed but flexible, shaped by motion and gravity. From its theoretical roots in Einstein's relativity to experimental confirmation using atomic clocks and satellites, the phenomenon has proven its reality and importance. Everyday applications like GPS systems and the experiences of astronauts show that time dilation is not just a mathematical curiosity but a factor with tangible effects. Philosophically, it challenges our perception of reality and the passage of time, inviting reflection on the universe and our place within it. As modern research continues to explore and test the limits of time dilation, we are reminded that the universe holds mysteries beyond ordinary experience. Understanding time dilation encourages curiosity, precision, and a willingness to rethink what seems familiar, revealing a world in which time is as dynamic and complex as the space it inhabits. Relativity of simultaneity is a central idea in modern physics that changes how we think about time. It tells us that two events happening at the same time for one observer may not happen at the same time for another observer. This idea matters because it challenges our everyday belief that time flows the same way for everyone. It also helps explain how the universe truly works at high speeds. Imagine two flashes of light happening far apart. You may think they occur together, but someone moving fast may disagree. This surprising thought pulls us into the strange but fascinating world of relativity. At its core, Relativity of simultaneity means that simultaneity depends on the observer's motion. In classical physics, time is absolute, so everyone agrees on what is simultaneous. In Einstein's theory of special relativity, time is not absolute. The key principle is that the speed of light is the same for all observers, no matter how fast they move. Because of this, observers moving relative to each other measure time differently. A common misconception is that this effect only comes from faulty clocks or delays in seeing signals. In reality, it is not about perception or reaction time. It is about how time itself is structured in the universe. The historical roots of this idea go back to the late 19th and early 20th centuries. Scientists were struggling to understand light and motion. Experiments showed that light always travels at the same speed, which conflicted with classical ideas. Albert Einstein addressed this problem in 1905 when he published his theory of special relativity. He built on earlier work by scientists like Galileo, Lorentz, and Maxwell. Over time, experiments supported Einstein's ideas, and the concept of simultaneity slowly changed. What began as a theoretical insight became a key part of modern physics. To understand how relativity of simultaneity works, consider two observers in relative motion. One observer stands on a platform while another rides a fast train. Suppose two lightning strikes hit both ends of the train track at the same time according to the observer on the platform. Light from both strikes reaches the platform observer together, so they conclude the events were simultaneous. For the observer on the train, things differ. They are moving toward one flash and away from the other. Since light speed is constant, the observer on the train receives one signal before the other and concludes the events were not simultaneous. The governing equations come from special relativity, especially the Lorentz transformations, which link space and time measurements between observers. These equations show that time and space are connected and not separate. Relativity of simultaneity may seem distant from daily life, but it has clear examples. In everyday speeds, the effect is extremely small, so we do not notice it. At speeds close to the speed of light, the effect becomes significant. Particle accelerators provide real demonstrations. Particles moving at high speeds experience time differently from laboratory observers. Another example involves satellites moving around Earth. Their motion causes small differences in time measurements compared to clocks on the ground. These differences confirm that simultaneity is not universal. The implications of this idea are wide-reaching. One important application is in the global positioning system. GPS satellites must account for relativistic effects, including differences in time, to give accurate positions. Without these corrections, navigation systems would fail. Scientifically, relativity of simultaneity reshaped physics by replacing absolute time with spacetime. It influenced fields such as cosmology, particle physics, and astrophysics. Beyond science, it also affects philosophy. It forces us to rethink what we mean by now and whether there is a single present moment shared by everyone. Modern research continues to explore the meaning and consequences of relativity. Experiments with ultra-precise clocks test relativistic predictions with high accuracy. Physicists also study how relativity fits with quantum mechanics, where time plays a different role. There are debates about how to describe simultaneity in curved spacetime, as in general relativity. Future research may reveal deeper connections between time, gravity, and quantum theory. These studies show that relativity of simultaneity is not just a historical idea but an active area of investigation. Despite its success, the concept brings challenges and paradoxes. One difficulty is understanding it intuitively, since human experience evolved at low speeds. The idea that there is no universal present can feel disturbing. Paradoxes like the twin scenario highlight how time differences arise between observers. While these situations seem contradictory at first, careful analysis resolves them. Still, open questions remain, especially about the nature of time itself. Is time fundamental, or does it emerge from deeper laws? Relativity does not fully answer this, but it frames the question clearly. In summary, relativity of simultaneity teaches us that time is not the same for everyone. It arises from the constant speed of light and the relative motion of observers. Historically, it marked a turning point in physics and replaced old ideas of absolute time. Through thought experiments, equations, and real-world applications, it has proven to be accurate and powerful. Its broader significance lies in how it changes our understanding of reality. The lesson is both scientific and philosophical. What seems obvious may not be universal, and the universe often demands that we question our deepest assumptions. Quantum entanglement is one of the most fascinating ideas in modern science. It describes a strange connection between particles that seems to go beyond ordinary experience. This topic is important because it challenges how we think about space, time, and cause and effect. It also plays a major role in new technologies that may shape the future. Imagine two tiny particles acting like close partners even when they are far apart. This surprising behavior pulls us into a deeper question about how nature truly works. At its core, quantum entanglement means that two or more particles become linked in such a way that the state of one particle is directly related to the state of the other. Even if they are separated by a great distance, measuring one particle instantly affects the other. The key principle here is that the particles cannot be fully described on their own. They must be described as a single system. A common misunderstanding is that information is sent faster than light. In reality, entanglement does not allow messages to travel instantly. Instead, it shows that the particles share a joint state that already exists before measurement. The idea of entanglement began in the early 20th century, when scientists were building the foundations of quantum mechanics. Albert Einstein, Boris Podolsky, and Nathan Rosen discussed it in a famous thought experiment in 1935. They questioned whether quantum theory was complete. Einstein referred to entanglement as a strange action at a distance because it seemed to break the rules of classical physics. Later, physicist Erwin Schrödinger gave the phenomenon its name and explored its meaning more deeply. Over time, experiments gradually supported the predictions of quantum theory, showing that entanglement is real and measurable. To understand how entanglement works, it helps to think about measurement in quantum mechanics. Before measurement, particles exist in a range of possible states. When two particles interact in a special way, their properties become linked. Once they are entangled, measuring one particle forces the system to settle into a definite state. The laws that govern this behavior come from quantum mechanics, especially the mathematics of wave functions and probabilities. These laws show that nature at very small scales does not behave like everyday objects. Instead, it follows rules that are statistical and interconnected. Real-world examples of entanglement are often seen in laboratories. Scientists create entangled photons using special crystals and lasers. When one photon is measured, the other shows a related result even if it is far away. Although we do not notice entanglement in daily life, its effects are observable in controlled experiments. Famous tests, such as those based on Bell's inequalities, have confirmed that entangled particles behave in ways that classical physics cannot explain. These experiments demonstrate that the universe is more deeply connected than it appears. The implications of quantum entanglement are wide-ranging. In technology, it forms the basis of quantum computing, where entangled particles can perform calculations more efficiently than classical computers for certain tasks. It is also essential for quantum cryptography, which promises extremely secure communication. In science, entanglement helps researchers understand the structure of matter and the limits of physical laws. Beyond physics, it influences philosophy by raising questions about reality, knowledge, and the nature of separation. It suggests that the universe may not be made of independent parts, but of relationships. Modern research on entanglement is very active. Scientists are studying larger and more complex systems to see how entanglement behaves beyond tiny particles. Recent experiments have entangled atoms, molecules, and even small mechanical systems. There are ongoing debates about how entanglement fits with gravity and the theory of relativity. Some researchers believe it may play a role in understanding black holes and the fabric of space itself. Future directions include building practical quantum networks and exploring whether entanglement can help explain why the universe has the structure we observe. Despite its success, quantum entanglement presents many challenges and paradoxes. One difficulty is understanding how entanglement fits with the idea of cause and effect. The instant correlation between distant particles seems to clash with common sense. Another puzzle is the measurement problem, which asks why a definite outcome appears when a measurement is made. There are also open questions about how entanglement disappears in large systems, a process called decoherence. These challenges show that our understanding of nature is still incomplete. In summary, quantum entanglement reveals a deep and surprising connection within the physical world. It shows that particles can be linked in ways that defy classical thinking. Its discovery changed the course of physics and opened doors to new technologies and ideas. More broadly, entanglement invites us to rethink what it means for things to be separate or connected. As research continues, it may lead us closer to a more unified understanding of reality and our place within it. Wave-particle duality is one of the most important ideas in modern physics. It explains that very small things, like light and electrons, do not behave only as particles or only as waves. Instead, they can show properties of both, depending on how they are observed. This idea changed how scientists understand nature at its deepest level. It shows that the universe does not always follow the simple rules we see in everyday life. By studying wave-particle duality, we learn that reality can be more complex and surprising than common sense suggests. This topic matters because it forms the foundation of quantum physics, which explains how atoms, light, and energy behave. To spark curiosity, imagine an object that can act like a solid ball in one experiment and like a spreading ripple in another. This strange behavior is not science fiction. It is a real feature of nature. At its core, wave-particle duality means that microscopic objects can behave as both waves and particles. A particle is usually thought of as a tiny object with a definite position, like a grain of sand. A wave is something that spreads out, like ripples on water. In classical physics, waves and particles are completely different. However, experiments show that light and matter do not fit into only one category. Key principles behind this idea include the role of observation and the limits of classical thinking. The way an experiment is set up determines whether wave-like or particle-like behavior is seen. A common misunderstanding is that an object is half wave and half particle at the same time in a simple sense. In reality, it does not switch back and forth like a costume change. Instead, it follows quantum rules that do not match everyday objects. The story of wave-particle duality begins with light. For many years, scientists argued about whether light was made of particles or waves. In the 17th century, some supported a particle view, while others supported a wave view. In the early 19th century, experiments with interference showed that light behaves like a wave. This seemed to settle the debate. Later, new discoveries changed everything again. At the start of the 20th century, experiments showed that light can also behave like particles of energy. Important contributors include Max Planck, Albert Einstein, and Louis de Broglie. Planck introduced the idea that energy comes in small packets. Einstein explained the photoelectric effect using particle-like light. De Broglie suggested that matter itself could have wave properties. Over time, experiments confirmed these ideas and built the modern understanding of quantum physics. Wave-particle duality works through the interaction between matter, energy, and measurement. When particles like electrons move freely, they can spread out and form wave patterns. When they interact with a detector, they appear as localized particles. This behavior is described using mathematical tools such as wave functions. These equations do not give exact positions but probabilities. One important equation is the Schrödinger equation, which describes how a quantum system changes over time. Another key relation connects wavelength with momentum, showing that faster particles have shorter wavelengths. The underlying principle is that nature at small scales is governed by probability rather than certainty. Observation plays a central role because measuring a system changes how it behaves. Examples of wave-particle duality can be seen in both simple and advanced experiments. In everyday life, this behavior is not obvious because large objects have extremely tiny wavelengths. However, in laboratories, the effects are clear. One famous experiment involves sending light or electrons through two narrow slits. Instead of forming two simple lines, they create an interference pattern typical of waves. Even when particles pass one at a time, the pattern slowly appears. This shows that each particle follows wave-like rules. Other demonstrations include electron microscopes, which rely on the wave nature of electrons to see very small details. These experiments provide strong evidence that wave-particle duality is real and measurable. The implications of wave-particle duality are wide-reaching. Many modern technologies depend on it. Devices such as lasers, semiconductors, and solar panels work because of quantum behavior. Electron microscopes allow scientists to study viruses and atoms. The scientific importance of this idea is enormous because it supports the entire framework of quantum mechanics. Without it, many accurate predictions about atomic behavior would fail. The impact also extends beyond physics. Chemistry relies on quantum models of atoms. Information science uses quantum ideas to explore new types of computing. Even philosophy is affected because wave-particle duality challenges traditional ideas about reality and knowledge. Modern research continues to explore wave-particle duality in new ways. Scientists study larger and more complex objects to see how long wave-like behavior can persist. Experiments with molecules and tiny mechanical systems push the boundary between the quantum and classical worlds. There are ongoing debates about the meaning of the wave function and the role of the observer. Some interpretations suggest that reality is fundamentally probabilistic, while others propose hidden structures beneath quantum behavior. Future research aims to better control quantum systems for technology, including quantum computers and secure communication. These efforts depend on a deep understanding of dual behavior. Despite its success, wave-particle duality raises serious challenges. One difficulty is that it does not fit easily with everyday logic. People naturally want clear categories, but quantum objects resist simple labels. There are also puzzles about how and when wave behavior turns into particle behavior. This is often called the measurement problem. Another challenge is explaining why large objects do not show obvious wave effects. Open questions remain about whether quantum rules apply universally or if new principles wait to be discovered. These challenges keep the topic active and important. In summary, wave-particle duality shows that light and matter can behave as both waves and particles. It emerged from centuries of debate and was confirmed by many experiments. The idea explains key observations and supports modern technology. Its broader significance lies in how it changes our view of reality. Nature at its smallest scale is not fixed and predictable in the classical sense. Instead, it is subtle, probabilistic, and deeply connected to observation. Reflecting on wave-particle duality reminds us that human intuition is limited and that learning science often means accepting ideas that feel strange but are proven true by evidence. The Heisenberg uncertainty principle is one of the most important ideas in modern physics. This principle explains a fundamental limit to what we can know about the physical world at very small scales. It shows that nature itself places boundaries on measurement, not because our tools are weak, but because reality behaves in a surprising way. The Heisenberg uncertainty principle is highly relevant because it changed how scientists understand matter, energy, and knowledge. Before this idea, physics aimed to predict everything exactly. After it, scientists learned that uncertainty is a basic part of the universe. This idea is important not only in physics but also in philosophy, as it challenges the belief that the universe is fully predictable. Imagine trying to observe a tiny particle that is smaller than anything you can see. The more carefully you look at it, the more it seems to slip away from precise knowledge. This strange behavior raises an important question. Can nature ever be known completely, or are there limits that cannot be crossed? The core idea of the Heisenberg uncertainty principle is that certain pairs of physical properties cannot both be measured exactly at the same time. The most common pair is position and momentum. Position tells us where a particle is, and momentum tells us how fast it is moving and in which direction. According to the principle, the more precisely we know the position of a particle, the less precisely we can know its momentum, and the reverse is also true. This is not caused by poor instruments or human mistakes. It is a natural rule of the quantum world. At very small scales, particles behave both like objects and like waves. Because of this wave-like nature, exact values for some properties simply do not exist at the same time. A common misunderstanding is that the principle only means scientists are careless or limited. Another misconception is that particles are fuzzy objects that randomly change their properties. In reality, the uncertainty principle describes limits in knowledge, not chaos without rules. The behavior of particles follows strict mathematical laws, even though the results include uncertainty. The uncertainty principle was discovered in the early 20th century during the development of quantum mechanics. At that time, scientists noticed that classical physics failed to explain the behavior of atoms and light. New theories were needed to describe the strange results of experiments at very small scales. The principle was introduced in 1927 by the German physicist Werner Heisenberg. He was one of the founders of quantum mechanics. Other important contributors include Max Planck, Niels Bohr, and Erwin Schrödinger. Each of these scientists helped build the framework that led to the uncertainty principle. The development began around 1900 with Planck's study of energy quanta. In 1905, Albert Einstein explained the photoelectric effect. During the 1920s, quantum mechanics rapidly evolved. By 1927, Heisenberg formally stated the uncertainty principle, which soon became a central part of modern physics. To understand how the uncertainty principle works, we need to look at how particles are observed. To see a particle, we must interact with it, often using light. Light comes in packets called photons. When a photon hits a tiny particle like an electron, it changes the particle's motion. This interaction makes it impossible to measure the particle without disturbing it. The uncertainty principle can be expressed using a mathematical relationship. It states that the uncertainty in position multiplied by the uncertainty in momentum must be greater than or equal to a small constant related to Planck's constant. This equation does not depend on technology or skill. It is a fundamental law of nature. The underlying idea is that particles are described by wave functions. A wave does not have a single exact location or speed. Instead, it spreads out. This wave behavior means that precise certainty in all properties is impossible. Nature allows probabilities, not perfect predictions. Although the uncertainty principle seems abstract, it has real-world examples. One example is the behavior of electrons inside atoms. Electrons do not move in neat circular paths. Instead, they exist in regions of probability called orbitals. This arrangement is a direct result of the uncertainty principle. Another example is everyday stability of matter. If electrons had exact positions and momenta, atoms would collapse. The uncertainty principle prevents this collapse and allows matter to exist in stable forms. Even though we do not notice it directly, this principle affects everything around us. Several experiments demonstrate the uncertainty principle. The famous double-slit experiment shows how particles create interference patterns like waves. Measurements of atomic spectra also confirm the limits predicted by the principle. These experiments provide strong evidence that uncertainty is real and measurable. The uncertainty principle has many technological applications. It plays a role in the design of electron microscopes, lasers, and semiconductor devices. Modern electronics depend on quantum behavior, which includes uncertainty. Scientifically, the principle changed how theories are built. Instead of exact predictions, quantum mechanics provides probabilities. This approach has been tested countless times and has never failed. It shows that uncertainty does not mean ignorance, but a deeper understanding of nature. The impact extends beyond physics. In chemistry, it explains atomic bonding. In philosophy, it raises questions about determinism and free will. It suggests that not all events are fixed in advance, which has influenced debates about the nature of reality. Modern research continues to explore the limits of the uncertainty principle. Scientists study quantum measurement, quantum information, and quantum computing. These fields investigate how uncertainty affects information and computation at the smallest scales. There are ongoing debates about how uncertainty should be interpreted. Some scientists argue about whether uncertainty reflects limits of knowledge or properties of reality itself. Different interpretations of quantum mechanics offer different answers, but all accept the uncertainty principle as valid. Future research aims to control and use uncertainty rather than eliminate it. Quantum technologies such as quantum cryptography rely on uncertainty to ensure security. Instead of being a problem, uncertainty becomes a powerful tool. Despite its success, the uncertainty principle raises challenges and paradoxes. One difficulty is understanding how the quantum world connects to the everyday world. Large objects do not seem uncertain in the same way as particles. Another puzzle involves measurement. When a particle is measured, its wave function appears to collapse into a definite state. How and why this happens is still unclear. This is known as the measurement problem. There are also open questions about whether uncertainty is truly fundamental or whether deeper laws exist. So far, all experiments support the principle, but science remains open to new discoveries. In summary, the Heisenberg uncertainty principle states that certain physical properties cannot be known exactly at the same time. It arises from the wave nature of particles and is a basic feature of quantum mechanics. It has been confirmed by experiments and is essential for understanding atoms and matter. The broader significance of the principle is that it reshapes our view of knowledge and reality. It teaches that limits are built into nature itself. This idea encourages humility in science and reminds us that understanding does not always mean complete control. The uncertainty principle invites us to reflect on the balance between knowledge and mystery. It shows that even in a universe governed by laws, there is room for unpredictability. This balance may be one of the most profound lessons science has to offer. Imagine opening a box and finding a cat that is somehow both alive and dead at the same time. This strange idea sounds impossible, yet it sits at the center of one of the most famous thought experiments in modern physics. Schrodinger's cat is not a real experiment done on animals. Instead, it is a powerful mental picture used to explain the strange rules of quantum mechanics. The topic matters because it challenges how we understand reality, observation, and knowledge. It forces us to ask whether the world exists in a fixed way or only becomes real when we look at it. This question pulls the audience in because it mixes science with deep philosophical curiosity about life, death, and certainty. At its core, Schrodinger's cat is a thought experiment that shows the idea of superposition. Superposition means that a quantum system can exist in more than one state at the same time. In the example, a cat is placed in a sealed box with a radioactive atom, a detector, and poison. If the atom decays, the detector triggers the poison and the cat dies. If it does not decay, the cat lives. According to quantum rules, before observation, the atom is both decayed and not decayed. As a result, the cat is described as both alive and dead. A common misunderstanding is thinking that the cat is literally half alive and half dead. The point is not the cat itself, but the strange behavior of tiny particles and how those rules seem to affect larger objects. The idea came from the early days of quantum mechanics in the 1930s. Erwin Schrödinger, an Austrian physicist, proposed the thought experiment in 1935. He was reacting to the Copenhagen interpretation of quantum mechanics, which suggested that particles do not have definite properties until they are measured. Other key contributors include Niels Bohr and Werner Heisenberg, who helped develop quantum theory. In the early 1900s, scientists discovered that classical physics could not explain atomic behavior. By the 1920s, quantum mechanics emerged. In the 1930s, debates grew stronger, leading Schrödinger to introduce his cat to highlight what he saw as a problem in the theory. To understand how the idea works, it helps to focus on the process inside the box. A radioactive atom has a chance to decay over time. Quantum mechanics describes this chance using probability, not certainty. The system follows the Schrödinger equation, which predicts how a quantum state changes. Before measurement, the system exists in a combination of all possible outcomes. This is the principle of superposition. Another key idea is wave function collapse. When an observation is made, the wave function collapses into one clear outcome. The underlying principle is that observation plays a central role in defining reality at the quantum level. Even though Schrödinger's cat is imaginary, similar ideas appear in real life at the quantum scale. For example, electrons can exist in multiple energy states at once. Light can behave as both a wave and a particle. These effects are observable through experiments like the double-slit experiment, where particles create interference patterns. Scientists have also created experiments with atoms and small molecules that show superposition. While we do not see cats in these states, the experiments confirm that quantum rules truly apply to nature. The implications of Schrödinger's cat reach far beyond a simple thought experiment. Quantum mechanics has led to technologies such as lasers, semiconductors, and medical imaging devices. The idea of superposition is essential for quantum computing, where bits can be both 0 and 1 at the same time. Scientifically, the cat highlights the measurement problem, which asks how and why observation changes outcomes. Its impact spreads to philosophy, influencing debates about realism and knowledge. It also affects discussions in logic and even art, where uncertainty and duality are common themes. Modern research continues to explore these questions. Scientists now study quantum decoherence, which explains how quantum systems lose superposition when interacting with their environment. Recent studies have shown superposition in larger systems than ever before, such as tiny mechanical objects. Ongoing debates include whether wave function collapse is real or just an appearance. Some interpretations suggest many worlds, where all outcomes happen in separate universes. Future research aims to connect quantum theory with gravity and to build practical quantum computers. Despite progress, serious challenges remain. One major difficulty is explaining how the clear world we see emerges from quantum uncertainty. There is a contradiction between smooth quantum equations and sudden collapse during measurement. Another puzzle is the role of consciousness. Some ask whether a human observer is needed for collapse, or if machines are enough. Open questions remain about the true nature of reality and whether quantum mechanics is complete or part of a deeper theory. In summary, Schrodinger's cat is a simple story with deep meaning. It introduces superposition, questions observation, and exposes limits in our understanding. Its broader significance lies in connecting physics with philosophy. The closing thought is that science does not only give answers. Sometimes it teaches us how strange and mysterious the universe truly is, and why curiosity remains essential for human progress. Quantum tunneling is a phenomenon in physics, where particles move through a barrier that, according to classical mechanics, they should not be able to pass. This concept challenges our everyday understanding of how matter behaves and opens doors to remarkable possibilities in both science and technology. It is a cornerstone of quantum mechanics, a field that investigates the behavior of particles at the smallest scales, where the rules are different from the ones we experience in daily life. Understanding quantum tunneling is crucial because it explains several physical processes that are fundamental to the functioning of the universe and modern technology. The importance of quantum tunneling extends beyond theoretical physics. It underpins the operation of devices like tunnel diodes and scanning tunneling microscopes and influences processes in nuclear fusion, which powers the stars. Exploring this phenomenon gives insight into the mysteries of atomic and subatomic worlds, offering a glimpse into a realm that defies common sense. To capture your imagination, imagine a ball rolling up a hill and passing through it as if it were a ghost. This seems impossible in everyday experience, but at the quantum level, particles can achieve just that. At its core, quantum tunneling occurs because particles at the quantum scale do not have definite positions or energies in the classical sense. Instead, they are described by a wave function, which provides the probability of finding the particle at a particular place. When a particle encounters a barrier, its wave function extends into and sometimes beyond the barrier, giving a non-zero probability that the particle will appear on the other side. This behavior contrasts sharply with classical physics, where a particle lacking sufficient energy cannot surpass a barrier. The key principle of quantum tunneling lies in the probabilistic nature of particles at the quantum level. Unlike a ball rolling over a hill, a particle does not need to have the energy to climb over a barrier completely. The probability of tunneling depends on factors like the height and thickness of the barrier and the particle's wavelength. A common misconception is that tunneling allows particles to gain energy or break physical laws. In reality, the particle's total energy remains the same, but the rules governing its movement are different because quantum mechanics allows a spread in its possible locations. The discovery of quantum tunneling traces back to the early 20th century, when physicists explored the limitations of classical mechanics. The phenomenon was first suggested to explain alpha decay, a process in which an atomic nucleus emits particles without sufficient classical energy to overcome the nuclear potential barrier. George Gamow was a pivotal figure in this development, applying quantum mechanics to explain how particles escape the nucleus through tunneling. His work, along with contributions from physicists like Friedrich Hund and Ralph Kronig, laid the foundation for understanding this counterintuitive process. The historical timeline shows that quantum tunneling has steadily evolved from a theoretical curiosity to a practical tool. In the 1920s, initial mathematical formulations explained nuclear decay. By the 1930s and 1940s, tunneling was recognized as essential in understanding electron behavior in solids. The latter half of the 20th century saw its application in electronic devices and microscopes, proving that quantum tunneling is not merely a mathematical abstraction but a phenomenon with tangible impact. Quantum tunneling works through the principles of wave-particle duality and probability. A particle behaves as both a particle and a wave, and the wave function determines where it might be found. When a particle approaches a barrier, the wave function penetrates the barrier and decreases exponentially with distance. If the wave function extends sufficiently, there is a measurable probability that the particle will appear on the other side. This mechanism is mathematically described by the Schrödinger equation, which governs the evolution of quantum states and allows calculation of tunneling probabilities. The underlying principles involve energy conservation and quantum uncertainty. Energy is never violated, but the uncertainty in a particle's position and momentum allows it to occupy regions forbidden in classical mechanics. These principles explain why tunneling can occur even when classical energy arguments suggest it should not. It also highlights the difference between deterministic classical physics and the inherently probabilistic nature of the quantum world. Quantum tunneling manifests in several observable ways. In everyday life, it explains phenomena such as the fusion reactions in the Sun, where hydrogen nuclei combine to form helium despite not having enough energy to overcome electrostatic repulsion. In technology, tunneling is essential in devices like tunnel diodes, which allow electrons to move through barriers to create fast electronic switching. Another example is the scanning tunneling microscope, which uses tunneling electrons to image surfaces with atomic resolution. Experiments repeatedly demonstrate tunneling, confirming that it is not just a theoretical construct but a measurable reality. The implications and applications of quantum tunneling are wide-ranging. In technology, it enables high-speed electronics and contributes to semiconductor operation. Scientific significance lies in its role in nuclear physics, astrophysics, and material science. By allowing particles to access regions of energy otherwise forbidden, tunneling explains processes that shape the universe, from radioactive decay to the generation of energy in stars. Its impact on other fields includes chemistry, where tunneling affects reaction rates at very low temperatures, and biology, where electron tunneling plays a role in photosynthesis and enzymatic activity. Modern research on quantum tunneling continues to uncover new insights. Studies explore tunneling in complex systems such as superconductors and nanostructures, where it affects conductivity and energy transfer. Ongoing debates concern the interpretation of tunneling times and the limits of applicability in macroscopic systems. Future directions include harnessing tunneling for quantum computing, where it can facilitate operations beyond classical limitations, and exploring its role in cosmological phenomena. Despite its successes, quantum tunneling presents conceptual challenges. Understanding how a particle can exist in two regions simultaneously or pass through a barrier without classical energy can be counterintuitive. There are apparent paradoxes, such as the tunneling time problem, which questions how long a particle takes to traverse a barrier. Open questions remain about the limits of tunneling in complex and macroscopic systems, pushing physicists to refine the theoretical framework and explore novel experimental setups. In summary, quantum tunneling reveals a world that defies classical intuition. It allows particles to move through barriers, explains natural processes like nuclear fusion, and underlies essential technologies such as tunnel diodes and scanning tunneling microscopes. The phenomenon highlights the probabilistic nature of quantum mechanics and demonstrates that energy conservation does not prevent particles from accessing classically forbidden regions. Its study enriches our understanding of physics and enables practical applications that shape modern life. The broader significance of quantum tunneling lies in its challenge to common sense and its demonstration of the deep principles governing the universe. It shows that the microscopic world follows rules different from our everyday experience, reminding us that reality at the smallest scales is far stranger than it appears. Reflecting on this, one can see that quantum tunneling is not just a scientific concept but a window into the mysteries of nature, offering lessons about the limits of classical reasoning and the richness of the universe beyond ordinary perception. A black hole is one of the most mysterious and fascinating objects in the universe. It is a region in space where gravity is so strong that nothing, not even light, can escape from it. The study of black holes has led scientists to question some of the fundamental laws of physics. One of the most intriguing questions in modern physics is the black hole information paradox, which asks whether information that falls into a black hole is permanently lost. Understanding this paradox is essential because it challenges our knowledge of quantum mechanics and general relativity. It also raises profound questions about the nature of reality and the universe itself. Imagine if everything you know could vanish without a trace. The black hole information paradox forces us to confront a similar question on a cosmic scale. To understand this paradox, we first need to grasp the basic concept of a black hole. A black hole forms when a massive star collapses under its own gravity at the end of its life. The core of the star compresses into a point called a singularity, surrounded by an event horizon, which is the boundary beyond which nothing can escape. The key principle behind a black hole is the interplay between gravity and spacetime, as described by Einstein's general theory of relativity. Gravity is so intense near the singularity that it warps spacetime to an extreme degree. One common misconception is that black holes suck in everything like a vacuum cleaner. In reality, they affect objects in their vicinity according to their gravitational pull, just like any other massive body. Objects can orbit a black hole safely if they remain outside the event horizon. The idea of black holes has a historical background that stretches back more than a century. The concept was first hinted at in the late 18th century by Jean Michel and Pierre-Simon Laplace, who suggested that a sufficiently massive star could have gravity so strong that light could not escape. The term black hole was later popularized in the 1960s, but the modern understanding developed gradually. Key contributors include Albert Einstein, who provided the theoretical foundation with general relativity, and Karl Schwarzschild, who found the first exact solution describing a black hole. Stephen Hawking made groundbreaking contributions by discovering that black holes can emit radiation, now known as Hawking radiation. The timeline of development shows that black holes evolved from a theoretical idea to an observable astrophysical phenomenon, with major discoveries spanning from the 1910s to the present day. The fundamental mechanisms of black holes are rooted in the laws of physics. Gravity bends the fabric of spacetime, and when it becomes extreme, a singularity forms at the core. The event horizon marks the point of no return. According to quantum mechanics, information about particles is preserved, but Hawking's work suggested that black holes radiate energy and could eventually evaporate completely. This process raises a crucial question: what happens to the information about matter that falls into a black hole? The governing laws include Einstein's field equations for gravity and the principles of quantum mechanics that describe subatomic particles. The underlying principle is that information in the universe cannot be destroyed, but black holes appear to challenge this notion, creating a paradox that scientists still try to resolve. In terms of real-world examples, black holes are not directly observable because they do not emit light. However, their presence can be inferred from their gravitational effects on nearby stars and gas. For instance, stars orbiting the center of our galaxy reveal the existence of a supermassive black hole called Sagittarius A star. Black holes can also produce observable effects through X-ray emissions when matter from a companion star falls toward them. Although black holes are extreme, understanding them has practical analogies. Scientists can simulate black hole conditions in laboratories using high-energy physics experiments, where energy and particle interactions mimic some aspects of black hole behavior. These experiments help us explore the principles that govern the universe on both cosmic and quantum scales. The implications and applications of studying black holes are vast. Technologically, the study of high-energy phenomena like black holes has led to advances in computing and particle physics research. More importantly, black holes have deep scientific significance. They test the limits of general relativity and quantum mechanics, pushing physicists to unify these theories into a single framework. Understanding black holes also impacts other fields, such as cosmology and information theory, by providing insights into how information, energy, and matter interact on the largest scales. The black hole information paradox, in particular, forces scientists to consider whether the universe is fundamentally deterministic or if information can be lost in extreme conditions. Modern research has advanced our understanding of black holes considerably. Recent studies have focused on the detailed mechanics of Hawking radiation and how it might preserve information. Scientists have proposed various solutions to the information paradox, including the idea that information may be encoded on the event horizon or released in subtle correlations within the radiation. Ongoing debates continue regarding the fate of information, the structure of the singularity, and whether alternative theories, like string theory, can provide a solution. Future directions include more precise observations using gravitational wave detectors and space-based telescopes, which could reveal new insights into black holes and the fundamental laws that govern them. Despite these advances, black holes present significant challenges and paradoxes. Conceptually, they challenge the principle that information is never lost, a cornerstone of quantum mechanics. Contradictions arise when predictions from general relativity and quantum theory seem incompatible, especially regarding singularities and event horizons. Scientists are also puzzled by questions about the ultimate fate of black holes, the role of quantum entanglement in preserving information, and whether new physics is required to resolve these issues. Open questions remain: can we reconcile these theories, and what will this tell us about the true nature of space, time, and reality? In conclusion, black holes are more than just cosmic curiosities. They represent the frontier where our understanding of physics is tested to its limits. The black hole information paradox challenges us to reconsider fundamental principles about information, gravity, and the structure of the universe. We have explored their formation, underlying mechanisms, observable effects, and the ongoing debates surrounding them. Modern research continues to probe these cosmic enigmas, offering a path toward resolving some of the deepest questions in physics. The broader significance of studying black holes lies in their ability to illuminate the hidden workings of the universe, revealing the delicate interplay between matter, energy, and information. Ultimately, contemplating black holes reminds us that the universe is vast and mysterious, and that understanding even a small part of it requires curiosity, observation, and the courage to question what we think we know. Entropy and the second law of thermodynamics are fundamental concepts in science that help us understand the natural tendency of energy and matter in the universe. These ideas are crucial for explaining why certain processes occur in nature and why some changes are irreversible. Understanding them allows us to predict how systems evolve over time, from simple chemical reactions to complex physical processes in stars and living organisms. Imagine a room where everything starts neatly arranged but gradually becomes disordered without any effort. This simple observation reflects a deeper principle that governs the behavior of energy and matter everywhere. Entropy is a measure of disorder or randomness in a system. It quantifies the number of ways a system can be arranged while still maintaining its overall properties. The second law of thermodynamics states that in an isolated system, the total entropy can never decrease over time. Energy spontaneously spreads from areas of high concentration to areas of low concentration, leading to a gradual increase in disorder. One common misconception is that entropy is only about chaos or messiness. In reality, it is a precise scientific concept that describes the distribution of energy and matter at a microscopic level. Another misunderstanding is that entropy can decrease naturally in an isolated system. The second law clearly shows that decreases in entropy require external energy input. The concept of entropy emerged during the 19th century when scientists studied heat engines and energy efficiency. Rudolf Clausius, a German physicist, first formulated the term entropy in 1865 while analyzing the limitations of heat conversion into work. Sadi Carnot had earlier examined the efficiency of engines and laid the groundwork for thermodynamic principles. Other contributors such as Lord Kelvin and Ludwig Boltzmann expanded the understanding of energy transformations and statistical interpretations of entropy. The development of these ideas followed a timeline beginning with Carnot's studies in the early 1800s, Clausius' formalization in the mid-1800s, and Boltzmann's statistical theory in the late 1800s. Together, these discoveries created a framework for modern thermodynamics and statistical mechanics. Entropy works through the natural tendency of energy to spread and distribute itself evenly. When energy flows from a hot object to a cold one, it is moving towards equilibrium, a state where no further net energy transfer occurs. This process is governed by equations such as delta S equals Q/T, where delta S represents the change in entropy, Q is the heat transferred, and T is the absolute temperature. This simple formula captures a profound truth: energy transfer always contributes to increasing entropy in an isolated system. Underlying this mechanism are principles such as the irreversibility of natural processes, the tendency of systems to approach equilibrium, and the statistical likelihood of certain arrangements over others. These principles explain why some transformations, like mixing hot and cold water, happen spontaneously, while others, like spontaneously separating mixed gases, are highly unlikely. Everyday life offers numerous examples of entropy at work. Ice melting in a glass of water demonstrates energy spreading from the warmer water to the colder ice, increasing disorder. Food left out becomes spoiled as molecules break down and spread more randomly. A burning candle converts solid wax into gas and light, dispersing energy into the surroundings. On a larger scale, weather systems, ocean currents, and even the life cycle of stars obey the second law of thermodynamics. Experiments in the laboratory can also demonstrate these effects. For instance, a gas expanding into a vacuum or heat flowing from a hot metal rod to a cooler one shows entropy increasing in real time. These observations confirm that energy naturally disperses and systems move towards greater disorder unless work is applied. The second law of thermodynamics has profound implications and applications. Technologically, it limits the efficiency of engines, refrigerators, and power plants. Engineers must account for energy loss due to increasing entropy when designing machines. Scientifically, it explains the arrow of time, the idea that time flows in a single direction from past to future. This law also influences fields such as chemistry, biology, and cosmology. For example, chemical reactions often proceed in the direction that increases entropy. Living organisms maintain local order by consuming energy, yet the total entropy of their environment still rises. Understanding entropy allows scientists to predict how systems evolve and to design technologies that work efficiently within these constraints. Modern research continues to explore the boundaries of entropy and the second law. Studies in statistical mechanics, quantum thermodynamics, and complex systems reveal subtle effects that were not apparent in classical physics. Scientists investigate how entropy behaves in microscopic systems, such as nanoscale engines or quantum computers. There are ongoing debates about the interpretation of entropy in the context of information theory, where it measures uncertainty rather than physical disorder. Future directions include understanding how entropy relates to black holes, the origin of the universe, and the fundamental limits of computation. These inquiries show that even well-established laws can lead to new discoveries when examined under different conditions. Despite its clarity, entropy presents conceptual challenges and paradoxes. One difficulty is reconciling microscopic reversibility with macroscopic irreversibility. At the level of individual particles, physical laws are reversible, yet the collective behavior of large systems leads to an apparent one-way flow of time. Contradictions such as Maxwell's demon challenge the second law by proposing thought experiments where entropy appears to decrease, yet careful analysis shows that overall entropy still increases when the demon's actions are included. Open questions remain about the ultimate fate of the universe and whether entropy will reach a maximum state known as heat death. These challenges make entropy not only a scientific concept but also a philosophical one, prompting reflections on order, chaos, and the passage of time. In summary, entropy and the second law of thermodynamics describe the natural tendency of energy and matter to move towards disorder. These concepts explain why processes like heat flow, chemical reactions, and diffusion occur spontaneously. The historical development of entropy highlights the contributions of Clausius, Carnot, Boltzmann, and Kelvin. Its mechanisms involve energy spreading, equilibrium, and statistical probabilities. Real-world examples from daily life to laboratory experiments illustrate these principles. The second law has technological and scientific significance, influencing engines, biological systems, and theories about the universe. Modern research continues to explore the limits and applications of entropy, revealing its role in quantum systems, information theory, and cosmology. Despite paradoxes and conceptual difficulties, entropy provides a framework for understanding the direction of natural processes and the arrow of time. Reflecting on these ideas helps us appreciate the deep connection between energy, matter, and the unfolding of events in the universe. Entropy teaches that order is temporary and energy naturally disperses, guiding everything from the smallest particle to the largest galaxy. Observing its effects in everyday life shows that change is constant, yet predictable within scientific laws. Understanding the second law of thermodynamics allows us to design better technologies, explain natural phenomena, and ponder fundamental questions about time and the universe. It reminds us that while humans can create order locally, the overall tendency of nature is towards greater disorder. This principle shapes not only scientific thought but also our philosophical understanding of existence and the flow of time. By studying entropy, we gain insight into both the physical world and the deeper patterns that govern reality. Dark matter is one of the most intriguing mysteries in modern physics and astronomy. It is a form of matter that does not emit, absorb, or reflect light, making it invisible to traditional telescopes. Despite being unseen, dark matter exerts a significant gravitational influence on the universe, shaping galaxies and clusters of galaxies. Understanding dark matter is crucial because it helps explain the formation and structure of the cosmos, offering insights into the unseen forces that govern celestial bodies. The concept captures the imagination of scientists and enthusiasts alike, prompting us to question what makes up most of the universe. To engage the audience, imagine a vast cosmic ocean in which galaxies drift as if caught in invisible currents. These currents are guided by a mysterious substance we cannot see, yet feel through its effects. Dark matter can be defined as a type of matter that interacts primarily through gravity and not through electromagnetic forces. Unlike ordinary matter, which consists of atoms, dark matter does not emit radiation that we can detect. Its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The key principles of dark matter involve gravitational influence, distribution in halos around galaxies, and its contribution to the overall mass of the universe. One common misconception is that dark matter is the same as black holes. While both are invisible, black holes are compact objects with extremely strong gravity concentrated in a small area, whereas dark matter is spread over vast regions and does not form stars or planets. Another misunderstanding is that dark matter can be observed directly. Instead, we detect its presence indirectly through its gravitational effects. The study of dark matter began in the early 20th century. The concept emerged when astronomers observed discrepancies between the visible mass of galaxies and the gravitational forces needed to keep stars in their orbits. In the 1930s, Fritz Zwicky studied the Coma cluster and found that the galaxies were moving faster than could be explained by the visible matter alone. He proposed the existence of unseen mass, which he called dark matter. Later, in the 1970s, Vera Rubin measured the rotation curves of spiral galaxies and confirmed that stars at the edges of galaxies rotated at unexpected speeds, reinforcing the idea that most of the mass was invisible. Key contributors to the study of dark matter include Fritz Zwicky, Vera Rubin, and Kent Ford. Over the decades, researchers have developed models and conducted experiments, creating a timeline that begins with observation, moves to theoretical understanding, and continues with modern experimentation and simulation. The fundamental mechanisms of dark matter involve its interaction through gravity while remaining invisible to electromagnetic observation. Dark matter affects the motion of galaxies, bends light through gravitational lensing, and contributes to the formation of cosmic structures. Its governing laws include Newtonian gravity and Einstein's general relativity, which describe how mass influences the curvature of spacetime. The underlying principles emphasize that although dark matter cannot be seen, its presence can be measured by its effect on other objects and radiation. For instance, the bending of light from distant galaxies as it passes near massive clusters provides evidence of dark matter's distribution. Dark matter has observable effects in the real world, especially on astronomical scales. While it does not influence everyday life directly, its role is essential for the stability and formation of galaxies. Without dark matter, galaxies would not hold together as they do, and stars could drift away from galactic centers. Gravitational lensing is a phenomenon where light from distant objects is bent around a massive cluster, allowing astronomers to map dark matter. Laboratory experiments, such as those using detectors deep underground or in space, aim to identify dark matter particles through rare interactions. Simulations of galaxy formation also demonstrate how dark matter shapes cosmic structures, providing visual evidence of its influence. The implications and applications of dark matter extend across scientific fields and technologies. In astrophysics, understanding dark matter is vital for models of galaxy formation, cosmic microwave background studies, and the evolution of the universe. It also plays a role in particle physics, as researchers search for hypothetical particles like WIMPs and axions that could constitute dark matter. Scientific significance lies in its ability to explain phenomena that ordinary matter cannot, providing a framework for unifying observations with theory. Dark matter research impacts cosmology, astronomy, and even mathematics, as models of dark matter require advanced computational methods. It influences philosophical thinking about the nature of the universe and encourages questioning of what we consider reality, showing that most of the universe is made of something we cannot see. Modern research and discoveries continue to advance our understanding of dark matter. Recent studies employ sophisticated telescopes, detectors, and simulations to uncover its properties. Experiments such as the Large Hadron Collider and underground dark matter observatories seek to detect particle candidates directly. Ongoing debates include the exact composition of dark matter, whether it consists of a single type of particle or multiple forms, and whether alternative theories of gravity could explain observations without dark matter. Future directions point toward more sensitive detectors, space-based observations, and advanced simulations that may finally reveal the true nature of this enigmatic substance. Researchers are also exploring the potential connections between dark matter and dark energy, which could reshape our understanding of the universe entirely. Dark matter presents several challenges and paradoxes. Conceptually, it is difficult to study because it cannot be observed directly, leading to reliance on indirect measurements. Contradictions arise when certain galactic observations do not align perfectly with predictions from simulations, prompting questions about the adequacy of current models. Open questions include whether dark matter interacts with itself or ordinary matter beyond gravity, its exact particle composition, and its role in the earliest moments of the universe. These puzzles challenge scientists to develop creative theories and improve experimental techniques, keeping the field dynamic and open-ended. In conclusion, dark matter is a central element in our understanding of the cosmos. Its key points include its invisibility, gravitational influence, contribution to galactic stability, and the ongoing search for its particle nature. The broader significance of dark matter lies in its capacity to explain the majority of the universe's mass, which remains hidden from direct observation. This understanding shapes the way we perceive the universe and drives inquiry into fundamental physical laws. Reflecting on dark matter reminds us that the universe contains layers of reality beyond what is visible, encouraging curiosity, rigorous investigation, and a willingness to embrace the unknown. It challenges humans to expand knowledge, refine scientific methods, and contemplate the profound mysteries that govern existence. Dark energy. Dark energy is one of the most mysterious and fascinating components of our universe. It is an invisible force that is causing the universe to expand at an accelerating rate. Understanding dark energy is crucial because it affects the fate of the cosmos and challenges our comprehension of fundamental physics. Its presence is inferred rather than directly observed, making it a topic that intrigues scientists and the public alike. Imagine looking up at the night sky and realizing that most of the universe is made up of something that cannot be seen, touched, or directly measured. This invisible energy shapes the cosmos in ways that are both profound and puzzling. At its core, dark energy is a form of energy that permeates all of space. It acts in opposition to gravity, pushing galaxies away from one another and causing the expansion of the universe to speed up rather than slow down. The key principle behind dark energy is that it has a negative pressure. While ordinary matter and radiation attract through gravity, dark energy repels, creating a force that grows stronger as space expands. A common misconception is that dark energy is similar to dark matter. While both are invisible and difficult to detect, dark matter exerts gravitational pull and helps hold galaxies together, whereas dark energy drives the expansion of space itself. The story of dark energy began in the early 20th century when scientists studied the motion of galaxies and the large-scale structure of the universe. Edwin Hubble discovered that galaxies were moving away from us, which suggested that the universe was expanding. For decades, it was assumed that this expansion would gradually slow due to gravity. However, in the late 1990s, astronomers studying distant supernovae found that the expansion was not slowing but accelerating. This surprising discovery introduced the concept of dark energy. Key contributors to our understanding include Albert Einstein, whose cosmological constant was an early theoretical prediction of a repulsive force, and modern astronomers such as Saul Perlmutter, Brian Schmidt, and Adam Rees, who provided observational evidence of acceleration. The timeline shows early theoretical work, observational confirmation in the 1990s, and ongoing research in the 21st century. Dark energy operates on a scale that affects the entire universe. Its behavior can be described through equations derived from Einstein's general theory of relativity. The cosmological constant, denoted by the Greek letter lambda, represents a simple model of dark energy that acts uniformly throughout space. In more complex models, dark energy can vary in strength over time and space. The underlying principle is that the universe contains a form of energy intrinsic to space itself. Unlike matter or radiation, this energy does not dilute as the universe expands. The laws of physics, particularly those of general relativity, govern how dark energy influences cosmic expansion and interacts with matter. Although invisible, the effects of dark energy can be observed in several ways. For instance, the accelerating expansion causes galaxies to drift apart more rapidly over time. This phenomenon affects the cosmic microwave background, which is the faint afterglow of the Big Bang. Observations of supernovae, galaxy clusters, and large-scale structures all provide indirect evidence of dark energy. Experiments using space telescopes, such as the Hubble Space Telescope, and surveys like the Dark Energy Survey, have helped map its influence. In everyday life, the effects are not directly noticeable, but the overall structure of the universe and its fate are shaped by this unseen force. Understanding dark energy has implications far beyond astronomy. In technology, studying cosmic expansion improves precision in instruments that measure distances and signals over vast scales. Scientifically, dark energy challenges our understanding of physics, prompting new theories that combine quantum mechanics and relativity. Its study impacts other fields such as cosmology, particle physics, and philosophy, where questions about the universe's origin, structure, and fate arise. The search for a unified theory that explains dark energy could lead to breakthroughs in our knowledge of fundamental forces and the nature of reality itself. Modern research continues to explore the mysteries of dark energy. Recent studies use advanced telescopes and simulations to understand its behavior and distribution. Scientists debate whether dark energy is a true cosmological constant or a dynamic field that changes over time. These debates influence models of the universe's ultimate fate, whether it will expand forever, slow down, or undergo a dramatic transformation. Future directions include more precise measurements of cosmic acceleration, exploration of alternative theories such as quintessence, and attempts to link dark energy with particle physics and quantum fields. Each new study brings us closer to understanding this enigmatic force while raising further questions. Despite progress, dark energy presents significant challenges and paradoxes. Conceptually, it is difficult to reconcile the idea of an energy that fills empty space and drives expansion with traditional physics. Observations indicate that dark energy constitutes roughly 70% of the universe, yet its exact nature remains unknown. Some contradictions arise in trying to unify quantum mechanics with general relativity to explain dark energy. Open questions include whether it is constant or evolving, whether it interacts with matter in unknown ways, and what its ultimate effect on the universe will be. These paradoxes make dark energy a topic that challenges both our imagination and our scientific tools. In conclusion, dark energy is a mysterious and powerful force that dominates the universe. It accelerates cosmic expansion, influences the large-scale structure of galaxies, and challenges fundamental physics. From its initial theoretical hints to modern observational studies, the journey of understanding dark energy reflects human curiosity and the drive to explore the unknown. Its study has significant implications for science and technology, shaping our comprehension of the cosmos and the fundamental laws that govern it. Looking ahead, dark energy will continue to push the boundaries of knowledge, encouraging scientists and thinkers to explore deeper questions about the universe, existence, and the ultimate destiny of all things. The quest to understand dark energy combines observation, theory, and imagination, reminding us that much of the universe remains a vast and intriguing mystery. Mass and energy are two concepts that seem separate at first glance, yet they share a deep and intrinsic connection. Today, we explore the idea that mass can be converted into energy and vice versa, a principle that underlies much of modern physics. Understanding this relationship is crucial because it reveals the hidden potential stored within matter, a potential that powers the sun, fuels nuclear reactors, and even forms the basis of some of the most significant technological advances in our world. Imagine a tiny particle holding the energy equivalent of thousands of tons of dynamite. This is not science fiction, but a reflection of the profound connection between mass and energy. To grasp this concept, we first define what mass and energy are. Mass is the measure of matter contained in an object, the quantity that resists changes in motion. Energy is the capacity to perform work, to move, to heat, or to cause change. The core principle linking these two is that they are interchangeable, bound by a simple yet powerful equation. This is not only a mathematical relationship but also a physical reality that permeates the universe. A common misconception is to think that mass and energy are always separate, or that energy exists independently of matter. In truth, every object has an intrinsic energy simply by having mass, a fact often overlooked in everyday life. The recognition of mass-energy equivalence did not emerge overnight. It originated from the study of relativity in the early 20th century. The principle was formulated as part of a broader understanding of how space, time, and matter interact. Many contributors played a role, but one name stands out: Albert Einstein. In 1905, he published a paper proposing that mass and energy are equivalent, connected by the equation E equals mc squared. This marked a turning point in physics, changing the way scientists perceive matter and its potential. Over the following decades, the idea gained empirical support and became a foundational concept, influencing the development of nuclear physics, cosmology, and particle science. Understanding how mass can transform into energy requires a look at the fundamental mechanisms behind it. At the atomic and subatomic levels, matter is composed of particles bound together by forces. When these particles are rearranged, combined, or split, the mass of the system can change slightly, and this change manifests as energy. The governing equation, E equals mc squared, expresses this relationship. Energy equals mass multiplied by the speed of light squared, revealing that even a small amount of mass corresponds to a very large amount of energy. The underlying principle is that mass and energy are two forms of the same reality. Conservation laws still apply, but they encompass both energy and mass, showing that what appears lost in mass is gained in energy, and vice versa. We can observe mass-energy equivalence in several real-world examples. In the Sun, nuclear fusion converts hydrogen into helium, releasing tremendous energy in the form of light and heat. This process is why the Sun shines and why life on Earth is possible. In nuclear reactors, a controlled version of this reaction converts a small amount of matter into energy that powers homes and industries. Even in everyday phenomena, the principle has subtle effects. When chemical bonds break during combustion or metabolism, tiny amounts of mass are transformed into energy, though the effect is usually too small to notice without precise instruments. Experiments in particle accelerators demonstrate the process more visibly. Colliding particles at high speeds can create entirely new particles, showing mass appearing from energy and energy appearing from mass. The implications of mass-energy equivalence are profound. Technologically, it enables the production of nuclear power, both as electricity and as fuel for spacecraft propulsion. Medically, radiation from decaying isotopes, which is a product of mass-energy transformation, is used in cancer treatment. Scientifically, the principle reshaped physics, linking previously separate areas like mechanics and thermodynamics to quantum theory. It also has philosophical significance, revealing the hidden potential within the universe, suggesting that matter is not inert but dynamic, holding energy waiting to be released. In other fields, such as chemistry and engineering, the understanding of energy mass conversion informs the design of safer reactors, more efficient engines, and innovative materials. Modern research continues to expand our understanding. Scientists study extreme environments such as neutron stars and black holes, where mass-energy equivalence operates at its limits. Recent studies examine how mass and energy behave under extreme conditions, including high-energy particle collisions in accelerators. Debates persist regarding the precise behavior of mass at quantum scales and in gravitational fields, where conventional equations may need modification. Researchers also investigate potential future applications, from advanced nuclear fusion to energy generation techniques that could surpass current limitations. Each discovery reinforces the principle while revealing new complexities, showing that the story of mass-energy equivalence is far from complete. Yet, the concept also presents challenges and paradoxes. Conceptually, it is difficult to reconcile the idea that a particle at rest contains immense energy. Contradictions arise when comparing classical physics, where mass is considered fixed, with relativistic physics, where mass can change under high-energy conditions. Certain phenomena, like the apparent creation of mass from pure energy in particle collisions, challenge intuition. Open questions remain about the fundamental nature of mass itself, the origin of energy in the universe, and the limits of conversion processes. These challenges highlight not only the complexity of physics but also the philosophical depth of understanding the universe. As we conclude, the key points are clear. Mass and energy are not separate entities but aspects of the same reality. The equation E=mc² encapsulates this truth, explaining processes from nuclear reactions to everyday chemical interactions. Historically, this understanding emerged from the work of early 20th-century physicists and has since transformed scientific thought. Mechanisms of mass-energy conversion operate at atomic and subatomic levels, producing observable effects in the natural and technological world. Applications span energy production, medical treatment, and advanced research, while ongoing studies continue to explore extremes and unresolved questions. The broader significance is profound. The principle challenges us to see matter not as static, but as a dynamic form of energy, revealing hidden potential in the universe. It provides a bridge between the tangible and the abstract, linking the physical to the philosophical. Reflecting on mass-energy equivalence invites a deeper appreciation of the universe and our place within it. Matter is not merely what we see and touch, but a storehouse of energy, waiting to be understood and harnessed. Recognizing this connection encourages both scientific inquiry and thoughtful reflection, reminding us that even the smallest particle holds within it a vast and powerful story of energy and existence. Electromagnetic induction is a fascinating phenomenon that forms the backbone of modern electricity generation and countless devices around us. It describes how electric currents can be produced in a conductor by changing magnetic fields. This principle is essential for understanding how generators, transformers, and many electrical appliances function, making it a cornerstone of both physics and engineering. Imagine a world without power stations, electric motors, or even your home lighting. The concept of electromagnetic induction brings life to such ideas and allows us to harness natural forces to serve human needs. At its core, electromagnetic induction occurs when a conductor, such as a wire, experiences a changing magnetic field, which induces an electric current in the conductor. This process is not limited to simple wires, it applies to coils, circuits, and even larger systems in power grids. The phenomenon relies on a few key principles. First, a changing magnetic field is necessary. A static magnetic field alone will not generate current. Second, the amount of induced current depends on factors such as the strength of the magnetic field, the speed at which it changes, and the number of loops in the conductor. Third, the direction of the induced current follows a specific rule that opposes the change in magnetic flux, ensuring a balance in energy transfer. One common misunderstanding is that any magnet near a wire automatically produces electricity. In reality, it is the change in magnetic environment, not merely the presence of a magnet, that drives current. Another misconception is that induction violates energy conservation, but in fact, the energy of the induced current comes directly from the work done to change the magnetic field. These clarifications help build an accurate picture of how the process works and why it is reliable for practical applications. The story of electromagnetic induction begins in the early 19th century, a period of rapid discovery in electricity and magnetism. The phenomenon was first observed by Hans Christian Ørsted in 1820, who found that electric currents could influence magnetic needles, demonstrating a link between electricity and magnetism. Building on this, Michael Faraday conducted a series of experiments in 1831 that established the foundation of electromagnetic induction. Faraday discovered that moving a magnet through a coil of wire induced a current, laying the groundwork for modern electrical engineering. Joseph Henry, working independently, made similar discoveries in the United States and contributed to understanding self-induction and electromagnetism. The development of electromagnetic induction unfolded through careful experimentation and theoretical interpretation. In the early 1800s, scientists were beginning to recognize the interplay of electric and magnetic forces. Ørsted's initial observation sparked curiosity, leading Faraday to systematically investigate magnetic flux and its influence on conductors. Faraday's law, formulated through these experiments, provided a quantitative way to describe induced electromotive force. By the mid-19th century, engineers and physicists had begun to apply these ideas, designing early generators, transformers, and induction coils. This timeline shows a progression from observation to experimentation, theory, and finally technological application. Understanding the mechanisms of electromagnetic induction requires a closer look at how magnetic fields interact with conductors. When a conductor moves through a magnetic field or when the field around a stationary conductor changes, the magnetic lines of force cut across the conductor. This motion creates an electromotive force, which drives electrons through the conductor, generating an electric current. The strength and direction of this current are governed by Faraday's law and Lenz's law. Faraday's law states that the induced voltage is proportional to the rate of change of magnetic flux, while Lenz's law dictates that the induced current will oppose the change causing it. These laws provide both predictive and explanatory power for a wide range of phenomena. The underlying principle of energy conversion is central to electromagnetic induction. Magnetic energy is transformed into electrical energy without any physical contact between the magnet and the wire. This principle allows for efficient energy transfer in generators, where mechanical motion is converted into electricity, and in transformers, which adjust voltage levels for safe distribution. Understanding these mechanisms clarifies why electromagnetic induction is both a natural and practical process, governed by consistent mathematical relationships and observable effects. Electromagnetic induction is observable in many everyday phenomena. One simple example is a flashlight dynamo, where turning a crank moves a magnet inside a coil to produce light. Electric guitar pickups convert string vibrations into electrical signals using similar principles. Induction cooktops heat pans without direct contact by generating currents in the metal base. Even traffic signals and electric trains use induction in various ways. Demonstrations in classrooms often include moving a magnet through a coil connected to a galvanometer, visually showing the current rise and fall, making the concept tangible and engaging. The implications of electromagnetic induction extend far beyond these simple examples. Technologically, it underpins electricity generation in power plants, from hydroelectric dams to wind turbines. Scientific research into magnetic fields, energy conversion, and electromagnetic waves relies on the principles of induction. It has influenced other fields such as medical imaging, where magnetic induction is critical in devices like MRI machines, and telecommunications, where signals are transmitted and received using induced currents. The ability to control and predict induced currents has revolutionized how humans interact with natural forces. Modern research continues to explore the limits and applications of electromagnetic induction. Studies investigate high-efficiency generators, superconducting materials, and new ways to harvest energy from environmental magnetic fluctuations. There are debates over optimal designs for wireless power transfer, minimizing losses in induction systems, and the potential for large-scale energy storage using electromagnetic principles. Researchers are also examining the intersection of quantum mechanics and induction to refine understanding of electron behavior in varying magnetic fields. These explorations promise new technologies and deeper comprehension of fundamental physics. Despite its robust theoretical framework, electromagnetic induction presents challenges and paradoxes that inspire further inquiry. Some concepts, such as self-induction and the behavior of eddy currents, can appear counterintuitive. The precise nature of energy transfer in complex systems sometimes raises questions about efficiency and losses. In educational settings, students often struggle with the abstract idea that invisible magnetic fields can produce tangible electric currents. Open questions include optimizing induction for renewable energy, reducing environmental impacts, and integrating emerging materials to enhance performance. These challenges highlight the dynamic and evolving nature of scientific understanding. Reflecting on electromagnetic induction, it becomes clear that this phenomenon is more than a scientific curiosity. It represents the profound connection between motion, magnetism, and electricity, illustrating how natural forces can be harnessed for human progress. The ability to convert energy forms reliably has transformed societies, enabling lighting, transportation, and communication on scales previously unimaginable. By studying both the practical and philosophical aspects of induction, we gain insight into the elegance of natural laws and the ingenuity of human application. In summary, electromagnetic induction is the process by which a changing magnetic field produces an electric current in a conductor. It relies on fundamental principles articulated through Faraday's law and Lenz's law, and it has been shaped historically by the contributions of Ørsted, Faraday, and Henry. The mechanisms involve motion and magnetic flux, and the effects are observable in daily life, from simple experiments to advanced technologies. Its applications extend to electricity generation, medical imaging, transportation, and beyond, while ongoing research explores new efficiencies and materials. Conceptual challenges encourage deeper understanding, and the broader significance of induction lies in its demonstration of nature's consistency and the human capacity to harness it for innovation. The story of electromagnetic induction exemplifies the intersection of science, technology, and philosophy, reminding us that even invisible forces can have tangible, transformative effects on the world around us. Superposition principle is one of the most important concepts in physics. It describes how different forces, waves, or quantum states can combine to produce a resultant effect. Understanding this principle is essential because it forms the basis of many physical phenomena and technologies that we encounter in everyday life. It helps us explain why waves interfere, how electrical circuits behave, and even how particles act in quantum mechanics. Imagine being able to predict the combined effect of multiple influences acting together. This is what the superposition principle allows us to do. At its core, the superposition principle states that when two or more influences act on a system at the same time, the total effect is equal to the sum of the individual effects. In other words, if you know how a system responds to each influence separately, you can find the combined response by simply adding them together. This principle applies to a variety of systems, including mechanical vibrations, sound waves, light waves, and electrical circuits. One key idea is that the system must be linear, meaning that the responses do not interfere with each other in a nonlinear way. A common misconception is that superposition only applies to waves, but it also applies to other linear systems such as forces and electrical currents. Another misunderstanding is that the principle works in all circumstances. In reality, it fails in systems that exhibit strong nonlinear behavior. The concept of superposition did not appear suddenly. Its origin can be traced back to the study of waves and vibrations in the 17th and 18th centuries. Early scientists noticed that when two waves met, they seemed to combine and produce a new wave pattern. Key contributors to the development of the superposition principle include Isaac Newton, who studied forces and motion, and Thomas Young, who explored interference of light. Leonhard Euler and Joseph Fourier also made significant contributions by developing mathematical tools to describe wave motion and linear systems. The timeline of development shows a gradual understanding of how complex phenomena can be broken down into simpler, additive effects. From early observations of sound and water waves to formal mathematical descriptions in the 19th century, the principle gradually became a cornerstone of classical physics. Superposition works through the idea that individual effects retain their identity when combined. For example, in wave mechanics, when two waves overlap, the displacement of the resulting wave at any point is simply the sum of the displacements of the individual waves. In electrical circuits, if two voltages are applied to a linear circuit, the total voltage response at any point can be calculated as the sum of the responses to each voltage separately. Mathematically, this is often expressed through linear equations. In quantum mechanics, the superposition principle allows a particle to exist in multiple states simultaneously, represented by the sum of all possible states. The underlying principles of superposition rely on linearity, additivity, and independence of responses. These ideas form the foundation for understanding how complex systems can be analyzed and predicted accurately. Everyday phenomena provide simple ways to observe the superposition principle. Sound waves provide clear examples, such as when multiple musical notes combine to form a harmonious chord. Light waves produce colorful patterns when passing through slits or overlapping films. Electrical circuits exhibit superposition when multiple current sources influence a network of resistors, allowing engineers to calculate voltages and currents efficiently. Experiments demonstrate the principle in tangible ways. For instance, the famous double-slit experiment shows how light or particles interfere with themselves when two paths are available, producing a pattern that reveals the sum of probabilities. Mechanical waves on a string or water surface show visible constructive and destructive interference when two waves meet. These demonstrations allow us to see abstract principles in action. The implications of the superposition principle are vast. In technology, it underlies the design of electrical circuits, communication systems, and audio engineering. Scientists use it to predict wave behavior in physics, study quantum systems, and solve problems in structural engineering. The principle also has scientific significance because it simplifies the analysis of complex systems. By breaking down interactions into additive effects, researchers can model and understand systems that would otherwise be too complicated. Its impact extends to other fields such as acoustics, optics, and quantum computing, where the ability to combine effects linearly is essential for practical applications. Superposition allows both theoretical understanding and practical problem solving. Modern research continues to explore superposition in new contexts. Recent studies investigate how quantum superposition can be maintained in large systems, a key challenge in developing quantum computers. Experiments with photons, electrons, and even molecules demonstrate that superposition remains valid at scales larger than previously thought. Ongoing debates include questions about the collapse of superposition in quantum measurement and the limits imposed by environmental interference. Future directions suggest that mastering superposition could revolutionize technology, allowing for faster computation, precise measurement, and new forms of communication. Researchers are also exploring hybrid systems where classical and quantum superpositions interact, creating complex behaviors that challenge our understanding. Despite its elegance, the superposition principle presents challenges and paradoxes. Conceptually, it can be difficult to understand that a particle can exist in multiple states at once or that forces can combine without losing their individual effects. Contradictions arise in nonlinear systems, where superposition no longer applies. In quantum mechanics, paradoxes like Schrodinger's cat illustrate the tension between superposition and observation. Open questions remain about how superposition behaves in complex or chaotic systems and how it might be harnessed without interference from external disturbances. These challenges highlight the subtle and sometimes counterintuitive nature of the principle, pushing scientists to refine their understanding. In summary, the superposition principle provides a powerful framework for understanding how multiple influences combine in linear systems. It explains phenomena in waves, electrical circuits, and quantum mechanics, offering predictive power and analytical clarity. By studying its mechanisms, history, and applications, we see how the principle connects simple observations to complex behaviors. The broader significance lies in its ability to simplify the study of nature, reveal underlying patterns, and enable technological innovation. Reflecting on superposition reminds us that many complex outcomes are the result of simpler additive effects, a concept that bridges classical and modern physics and continues to inspire scientific exploration. Light is one of the most fundamental aspects of our universe, and at its core lies the photon. Today we will explore the photon, a particle that carries light and energy across the cosmos. Understanding photons is essential because they form the basis of many technologies and influence how we perceive and interact with the world. From the screens we use daily to the intricate mechanisms of quantum computing, photons play a critical role. Imagine for a moment the sunlight streaming through a window or the glow of a distant star. These experiences are made possible by countless photons traveling vast distances. This invisible yet powerful particle shapes both our physical environment and our scientific understanding. A photon can be defined as a discrete packet of electromagnetic energy. It is the fundamental particle of light and other forms of electromagnetic radiation. Photons exhibit both particle-like and wave-like behavior, a concept known as wave-particle duality. They have no rest mass but carry energy and momentum, allowing them to interact with matter in specific ways. The key principles of photons include quantization, meaning energy is transmitted in fixed amounts, and the speed of light, which is a universal constant in a vacuum. Despite their ubiquity, photons are often misunderstood. Many people think light is only a wave, not realizing that it can also act as a particle depending on the circumstances. Others assume photons exist only in visible light, but they actually encompass the entire electromagnetic spectrum from radio waves to gamma rays. The story of the photon begins in the early 20th century with the study of light and radiation. The idea that light could behave as a particle was first suggested by Albert Einstein in 1905. He proposed that light consists of discrete packets of energy to explain the photoelectric effect, a phenomenon where light striking a metal surface releases electrons. Einstein built upon Max Planck's earlier work, where Planck introduced the concept of quantized energy to solve problems with blackbody radiation. Key contributors to the development of photon theory include Niels Bohr, whose model of the atom relied on quantized energy levels, and Arthur Compton, who demonstrated the particle nature of photons through scattering experiments. The understanding of photons grew over several decades, evolving from a theoretical idea to a cornerstone of quantum physics. By the 1920s and 1930s, the photon was firmly established as a real and measurable entity within the scientific community. Photons operate through mechanisms that bridge energy, matter, and light. They propagate as electromagnetic waves but transfer energy in discrete amounts, called quanta. This duality allows photons to interact with electrons, atoms, and molecules, resulting in phenomena such as reflection, refraction, and absorption. The governing laws include Maxwell's equations, which describe the behavior of electromagnetic waves, and Einstein's relationship between energy and frequency, which quantifies the energy carried by a photon. At its essence, the principle underlying photons is that energy can be both continuous and discrete, challenging classical intuitions. Photons do not slow down in a vacuum, and their energy depends solely on frequency. This interplay of simplicity and complexity is what makes photons both approachable and intellectually profound. In daily life, photons are everywhere. When sunlight warms your skin, photons are transferring energy from the sun to your body. When we see colors, photons are interacting with our eyes, and different wavelengths correspond to different colors. Lasers, LED screens, and fiber optic communications all rely on precise control of photons. Experiments that reveal photon behavior include the double-slit experiment, which demonstrates wave-particle duality, and the photoelectric effect, which shows the particle nature of light. Even something as simple as a camera capturing an image relies on photons striking a sensor. Observing how light bends through a prism or creates rainbows offers a tangible way to understand the invisible movement of photons around us. The study of photons has profound implications and applications. In technology, they enable telecommunications, medical imaging, and quantum computing. Fiber optics use photons to transmit data across continents at incredible speeds. In medicine, laser treatments rely on precise photon interactions with tissues. Scientifically, photons allow researchers to probe the structure of atoms and molecules. They also facilitate experiments that test the limits of quantum mechanics. The impact of photon research extends beyond physics into chemistry, biology, and engineering, influencing fields as diverse as material science and astronomy. The control and understanding of photons have transformed modern life, shaping both practical innovations and theoretical advances. Modern research continues to reveal surprising properties of photons. Scientists study phenomena such as entanglement, where two photons can be linked in a way that the state of one instantly affects the other, regardless of distance. Recent studies investigate single photon sources for quantum computing and secure communications. Ongoing debates explore the fundamental nature of light, including whether it is more accurately described as a particle, a wave, or a unified entity that defies classical categories. Future directions involve manipulating photons for advanced technologies, such as photonic circuits that might one day replace electronic circuits, and exploring photons' role in fundamental physics, including cosmology and the behavior of dark energy. Despite extensive knowledge, photons present challenges and paradoxes. Conceptual difficulties arise from their dual nature, which defies classical intuition. Experiments like the delayed choice experiment show that photons can behave in ways that seem to depend on future measurement choices, creating philosophical questions about causality and observation. Contradictions emerge when trying to reconcile the particle and wave descriptions simultaneously, a puzzle that is central to quantum mechanics. Open questions include the nature of light in extreme conditions, the limits of photon-based technologies, and how photons interact with dark matter or other unknown components of the universe. These challenges illustrate that while photons are well studied, they continue to inspire deep scientific and philosophical inquiry. In conclusion, photons are fundamental to both our understanding of the universe and the technology that shapes modern life. They are discrete packets of light energy, essential to phenomena ranging from the warmth of the sun to the operation of advanced electronics. Their discovery and study involved key figures such as Einstein, Planck, Bohr, and Compton, and their behavior is governed by principles that blend classical and quantum ideas. Photons influence daily life through visible effects and technological applications while continuing to challenge scientists with paradoxes and mysteries. The research on photons opens doors to new technologies and deeper understanding of nature, making them a subject of ongoing fascination. Reflecting on the role of photons allows us to appreciate both the complexity and the elegance of the universe. By studying photons, we gain insight into the smallest units of light, the deepest principles of physics, and the vast connections between energy, matter, and observation. Their presence is invisible yet undeniable, and their study remains one of the most rewarding pursuits in science, bridging the tangible world we interact with and the abstract laws that govern reality. Gravitational waves are ripples in the fabric of space and time, a phenomenon that stretches across the universe. They are produced by some of the most energetic events in the cosmos, such as colliding black holes or exploding stars. Studying these waves helps us understand the invisible forces that shape our universe and challenges the limits of human knowledge. Imagine the universe as a vast ocean and gravitational waves as ripples traveling through it. Detecting these ripples allows scientists to listen to events billions of light-years away, revealing secrets that would otherwise remain hidden. At its core, a gravitational wave is a disturbance in spacetime caused by accelerating massive objects. When enormous bodies like black holes orbit each other or collide, they create fluctuations that propagate outward at the speed of light. These waves compress and stretch space as they pass, although the effect is extremely subtle and can only be detected with highly sensitive instruments. The concept arises from Albert Einstein's theory of general relativity, which describes gravity not as a force but as the curvature of spacetime. A common misconception is that gravitational waves are like sound waves traveling through air. In reality, they move through the fabric of space itself and can pass through matter almost unaffected. The idea of gravitational waves originated in the early 20th century. Einstein first predicted their existence in 1916 while developing his general theory of relativity. His equations suggested that massive, accelerating objects would produce waves that ripple through spacetime. Initially, these waves were thought to be too weak to detect, leading many scientists to doubt their existence. Over time, theoretical work clarified their properties, and experimental techniques gradually advanced. Key contributors to this journey include Joseph Weber, who designed the first detectors in the 1960s, and modern teams like LIGO and Virgo that made the first direct detections in the 21st century. The timeline of development spans decades, beginning with theoretical predictions, followed by indirect evidence, and culminating in direct observation in 2015, confirming Einstein's century-old prediction. Gravitational waves function by carrying energy away from accelerating masses in a specific pattern. As two massive objects orbit each other, they create a changing gravitational field that radiates outward in wave form. The governing law is derived from Einstein's field equations, which relate the curvature of spacetime to the energy and momentum of matter. These waves propagate at light speed and are characterized by their amplitude, frequency, and polarization. The underlying principle is that mass and energy are connected to spacetime geometry, and any rapid change in this geometry produces waves that travel through the universe. Understanding these mechanisms requires grasping the interplay between energy, mass, and the shape of space itself. Although gravitational waves originate in extreme cosmic events, they have connections to everyday phenomena. The principles that govern these waves are also relevant in understanding how massive bodies interact and influence each other gravitationally. Observing their effects requires sophisticated instruments like interferometers, which measure tiny distortions in space caused by passing waves. Demonstrations in the laboratory may include models that show how vibrations propagate through elastic media, illustrating wave behavior in a simplified way. While the actual effects of gravitational waves on Earth are minuscule, detecting them allows scientists to confirm theoretical predictions and explore events that occurred millions or billions of years ago. The discovery of gravitational waves has profound implications. Technologically, the methods developed for detection have advanced laser measurement techniques, vibration isolation, and data analysis methods that can be applied in other fields. Scientifically, the observations allow for testing the limits of general relativity under extreme conditions, helping to refine our understanding of gravity. They also provide insight into phenomena that were previously invisible, such as black hole mergers or neutron-star collisions. Beyond physics, these findings impact astronomy, cosmology, and even philosophy, as they force us to reconsider our understanding of the universe as a dynamic and interconnected entity. Modern research in gravitational waves continues to expand rapidly. Recent studies have not only confirmed additional events, but have also begun to provide information about the population of black holes and neutron stars. Researchers are investigating the potential for gravitational waves to reveal information about the early universe, possibly offering clues about the moments after the Big Bang. Ongoing debates include the interpretation of subtle signals, the limitations of current detectors, and how to integrate gravitational wave observations with electromagnetic signals. Future directions aim at building more sensitive instruments, expanding detection networks, and exploring low-frequency waves that could reveal even more about galactic and cosmological processes. Despite their fascinating nature, gravitational waves present challenges. Conceptually, it is difficult to visualize a ripple in space itself, as it differs fundamentally from familiar waves in water or sound. Contradictions arise when trying to reconcile quantum mechanics with general relativity, leaving open questions about how gravity operates on the smallest scales. Detecting these waves also pushes the boundaries of engineering and experimental physics, requiring instruments capable of measuring changes smaller than a fraction of a proton's diameter. Open questions include the nature of sources that have not yet been observed, how waves interact with extreme environments, and what new physics might be revealed by future discoveries. In summary, gravitational waves are ripples in spacetime that provide a unique window into the universe. Their study bridges theoretical physics and observational astronomy, allowing scientists to test fundamental laws and explore cosmic phenomena that were once beyond reach. The detection of these waves represents both a triumph of human ingenuity and a reminder of the vastness and complexity of the cosmos. Gravitational waves show that the universe is not static, but alive with motion and energy, challenging us to expand our understanding of reality. As we continue to explore these ripples, we gain not only knowledge but also a profound appreciation for the interconnectedness of all things in the universe. They inspire curiosity, invite reflection, and promise discoveries that could redefine our perception of space, time, and existence itself. String theory is a fascinating branch of theoretical physics that aims to explain the fundamental nature of the universe. At its core, string theory proposes that the most basic building blocks of reality are not point-like particles but tiny, vibrating strings. These strings are so small that they are beyond the reach of current experimental detection, yet their vibrations determine the properties of all matter and forces in the universe. Understanding string theory is crucial for scientists because it attempts to unify all forces of nature, including gravity, which has remained a challenge for decades. The idea may seem abstract, but it has profound implications for our understanding of space, time, and the very fabric of reality. Imagine a universe where everything, from the smallest electron to the largest galaxy, is composed of minuscule strings vibrating in a cosmic symphony. The basic concept of string theory revolves around the idea that all particles are manifestations of one-dimensional strings. Instead of thinking of electrons, quarks, or photons as point-like objects, string theory describes them as loops or segments of energy that vibrate at specific frequencies. The vibration of each string corresponds to a different particle, much like different notes produced by strings on a musical instrument. The key principles include the existence of multiple dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. According to string theory, the universe may have 10 or even 11 dimensions, with the extra dimensions being compactified and hidden from our perception. One common misconception is that string theory has been proven. In reality, it remains a theoretical framework with limited direct experimental evidence, but its mathematical consistency makes it a promising candidate for a unified theory. The historical background of string theory traces back to the late 1960s. The original motivation was not to unify forces but to explain the strong nuclear force. Researchers noticed that the patterns of particles produced in high-energy collisions could be modeled by vibrating strings. Early pioneers such as Gabriele Veneziano and Leonard Susskind developed the first mathematical formulations, which laid the groundwork for modern string theory. Over time, the theory evolved from a model for hadrons to a potential framework for a theory of everything. Key contributors include John Schwartz and Michael Green, who demonstrated that string theory could be free of certain inconsistencies and compatible with gravity. The timeline of development shows gradual progress from the dual resonance models of the 1960s to the 5 consistent string theories identified in the 1980s, and eventually to the unifying concept of M-theory in the 1990s, which suggested that all string theories are connected. Understanding the fundamental mechanisms of string theory requires examining how strings behave. Strings can be open or closed loops, and their vibrations determine the particle type and its properties, such as mass and charge. The theory is governed by complex mathematical equations derived from quantum mechanics and general relativity. For example, the equations describe how strings propagate through spacetime and interact with one another. One underlying principle is that the universe is fundamentally quantum mechanical, meaning that uncertainty and probabilistic behavior are essential features of reality. Another principle is that all forces, including gravity, can be described within the same framework, which makes string theory unique compared to other models. The idea of duality is also central, showing that different perspectives of string behavior can lead to equivalent physical descriptions. Real-world examples of string theory are subtle because the strings themselves are too small to observe directly. However, the effects of string theory could influence phenomena such as the behavior of black holes and the early universe. For instance, certain predictions of string theory help explain the entropy of black holes and the microscopic structure of spacetime near their event horizons. Observable effects might also appear in the patterns of cosmic radiation or in the outcomes of high-energy particle collisions, though these remain indirect hints. Experiments such as the Large Hadron Collider provide opportunities to test some aspects of the theory, like the existence of extra dimensions or supersymmetric particles, but definitive evidence has yet to be found. Thought experiments and computer simulations allow scientists to explore the consequences of string vibrations in controlled theoretical environments. The implications and applications of string theory extend beyond pure physics. Technologically, understanding fundamental forces could lead to breakthroughs in quantum computing or materials science, though practical applications remain speculative. Scientifically, string theory is significant because it offers a unified framework for all known interactions, potentially solving long-standing puzzles about gravity and quantum mechanics. It also influences other fields such as cosmology, by providing models for the origin and evolution of the universe, and mathematics, through the discovery of new geometrical structures and symmetry principles. By linking seemingly unrelated phenomena, string theory has the potential to reshape our comprehension of reality, guiding future exploration of both the very large and the very small. Modern research in string theory continues to push boundaries. Recent studies explore topics such as holographic duality, which suggests a deep connection between theories of gravity and quantum field theories. Scientists are investigating how string theory might explain dark matter and dark energy, components of the universe that remain mysterious. Ongoing debates revolve around the testability of the theory, with some critics arguing that the lack of experimental confirmation challenges its scientific status. Nevertheless, proponents emphasize the theory's internal consistency and its ability to resolve theoretical problems. Future directions include refining M-theory, developing computational models to simulate string behavior, and seeking indirect observational evidence that could confirm the predictions of the theory, particularly in astrophysical and cosmological contexts. Despite its promise, string theory faces significant challenges and paradoxes. Conceptual difficulties arise from the high number of dimensions it requires, which are not directly observable. Additionally, the mathematics involved is extremely complex, demanding advanced knowledge of geometry and topology. Contradictions or puzzles include the problem of vacuum selection, as string theory allows for a vast landscape of possible universes, each with different physical laws. This leads to the question of why our universe has the properties it does. Open questions also involve the reconciliation of string theory with the principles of quantum gravity and the search for experimental signatures that could distinguish it from other theoretical frameworks. These challenges highlight both the ambition and the difficulty of constructing a complete theory of everything. In conclusion, string theory represents one of the most ambitious efforts to understand the universe at its most fundamental level. By proposing that all particles are vibrating strings, it unifies seemingly disparate forces under a single theoretical framework. The historical development of string theory, from its origins in particle physics to modern explorations of M-theory, reflects the collaborative and evolving nature of scientific inquiry. The fundamental mechanisms, governed by quantum principles and complex equations, provide a coherent description of matter, energy, and spacetime. Real-world examples and experiments hint at the theory's potential relevance, even if direct observation remains out of reach. The implications for technology, science, and mathematics are profound, offering new ways to understand and manipulate the universe. Contemporary research continues to explore its predictions, test its boundaries, and address its paradoxes, demonstrating the dynamic and ongoing nature of this field. Despite its conceptual and experimental challenges, string theory encourages a philosophical reflection on the nature of reality, suggesting that the universe may be far more intricate and interconnected than previously imagined. Ultimately, studying string theory invites curiosity, critical thinking, and a willingness to confront the deepest mysteries of existence, inspiring future generations of scientists and thinkers to explore the cosmic symphony of vibrating strings. Quantum foam is a concept in physics that describes the fundamental structure of space at the smallest scales. It suggests that space is not smooth and continuous, but instead fluctuates at extremely tiny scales. Understanding quantum foam is essential for comprehending the nature of the universe, as it connects quantum mechanics and general relativity, two pillars of modern physics. This idea challenges our everyday perception of space as a calm and empty void and invites us to imagine a world that is vibrant and constantly changing at scales far beyond direct observation. By exploring quantum foam, we gain insight into the fabric of reality and the limits of our current scientific knowledge. At its core, quantum foam refers to the turbulent, ever-changing nature of spacetime at the Planck scale, which is about 1/10,000,000,000th of a trillionth of a meter. At this scale, energy fluctuations create a foam-like structure, where tiny bubbles of space and time appear and vanish almost instantly. This concept arises from combining quantum mechanics with the theory of general relativity. Quantum mechanics tells us that energy cannot remain perfectly stable and that even empty space is subject to random fluctuations. General relativity shows us that energy influences the shape of spacetime. Together, they imply that on the smallest scales, spacetime itself becomes frothy and unstable. A common misconception is that quantum foam can be observed directly with current instruments, but it exists at scales far smaller than even the most powerful microscopes can detect. It is a theoretical framework supported indirectly through mathematical models and the effects it may have on high-energy particles. The concept of quantum foam emerged in the mid-20th century as physicists attempted to reconcile quantum mechanics with the geometry of spacetime. The term was coined by John Wheeler, a prominent theoretical physicist, who proposed that space at the smallest scales is not smooth but exhibits wild fluctuations. Wheeler built upon earlier work by Max Planck, whose discovery of the Planck length and Planck time provided natural limits for the scales at which quantum effects dominate gravity. Richard Feynman, a later contributor, developed path integral formulations that reinforced the idea that all possible histories of a particle contribute to quantum phenomena, indirectly supporting the notion of fluctuating spacetime. Over the decades, the concept has been refined through theoretical research, simulations, and indirect experimental evidence, gradually becoming an integral part of modern physics discussions. Quantum foam functions through the interaction of quantum mechanics and general relativity. At very small scales, the uncertainty principle indicates that energy can fluctuate dramatically over extremely short periods. These fluctuations cause the geometry of spacetime to vary constantly, forming tiny virtual black holes, wormholes, and bubbles. Equations from quantum field theory and general relativity describe these interactions, though a complete mathematical description of quantum foam remains elusive due to the challenge of unifying these two theories. The underlying principle is that the vacuum is not empty but dynamic, full of ephemeral events that briefly create and destroy structures in spacetime. This mechanism implies that what we consider empty space is actually a seething sea of activity at the smallest scales, challenging our classical notions of reality. In everyday life, the effects of quantum foam are not directly observable, but they may influence phenomena at extreme energies or distances. For instance, tiny fluctuations in spacetime could affect the behavior of cosmic rays traveling across the universe or cause slight distortions in the propagation of light over astronomical distances. Experiments such as the observation of gamma-ray bursts have been proposed to detect minute effects that could be attributed to quantum foam, though results remain inconclusive. Laboratory experiments using particle accelerators and quantum optics have also been suggested to probe the limits of spacetime structure. While these phenomena are subtle, they underscore that quantum foam is not merely a theoretical curiosity but a feature of the universe that could have measurable consequences. Quantum foam has implications for both technology and science. Understanding its properties could help physicists develop a theory of quantum gravity, a goal that has remained elusive for decades. In terms of scientific significance, studying quantum foam challenges our concepts of space, time, and reality itself, offering potential insights into the origins of the universe. Some researchers speculate that harnessing knowledge of spacetime fluctuations could influence future technologies, perhaps enabling advances in quantum computing or precision measurements. Additionally, the study of quantum foam intersects with fields such as cosmology, particle physics, and even philosophy, prompting questions about the nature of existence and the limits of human knowledge. Modern research continues to explore the properties and implications of quantum foam. Recent studies focus on high-energy cosmic phenomena, theoretical simulations, and the search for indirect evidence through gravitational waves and light propagation. Researchers debate whether quantum foam could leave detectable signatures in the cosmic microwave background or if it might influence black hole physics. Ongoing debates also consider whether spacetime is fundamentally discrete or continuous, a question intimately linked with quantum foam. Future directions involve combining quantum mechanics and general relativity into a consistent framework, possibly through approaches like string theory or loop quantum gravity. These efforts aim to move beyond theoretical speculation toward concrete models that can be tested experimentally. Despite advances, quantum foam presents conceptual challenges and paradoxes. One difficulty is visualizing a structure that is smaller than atoms and constantly fluctuating. The apparent contradictions between quantum mechanics and general relativity become most pronounced at the Planck scale, where neither theory alone can fully describe the behavior of spacetime. Open questions include whether quantum foam could influence macroscopic phenomena, how it affects the information content of space, and whether it can explain singularities such as those found inside black holes. Philosophical questions also arise about the nature of reality when space itself is not continuous, forcing a reconsideration of fundamental assumptions about existence. In summary, quantum foam represents a dynamic, fluctuating structure underlying the fabric of space. It highlights the interplay between quantum mechanics and general relativity and challenges the notion of empty, static space. From its historical development to its fundamental mechanisms, quantum foam has expanded our understanding of the universe and continues to drive scientific inquiry. While direct observation remains beyond current capabilities, indirect evidence and theoretical models provide insight into its nature. The study of quantum foam connects to cosmic phenomena, experimental physics, and technological prospects, demonstrating that even the tiniest structures can have profound significance. The broader significance of quantum foam lies in its ability to shape our understanding of reality. It forces scientists to rethink the continuity of space, the limits of observation, and the foundations of physical law. By examining quantum foam, we explore not only the structure of the universe but also the boundaries of human knowledge, bridging the gap between the observable and the theoretical. The concept encourages curiosity, rigorous investigation, and philosophical reflection, reminding us that the universe is far more intricate than it appears at first glance. Quantum foam embodies the mystery and complexity at the heart of nature, inspiring ongoing research and the pursuit of a deeper comprehension of existence. Vacuum energy is a fascinating concept in physics that challenges our understanding of empty space. At first glance, emptiness may seem like nothing exists there, but vacuum energy suggests that even in a perfect vacuum, there is a constant, underlying energy present. This invisible energy is not just a theoretical idea, it has deep implications for the universe, from the behavior of tiny particles to the expansion of the cosmos itself. Understanding vacuum energy helps us explore the fundamental nature of reality and pushes the boundaries of science in ways that are both exciting and mysterious. Imagine a space where nothing seems to exist, yet it hums with energy, waiting to be discovered. That is the essence of vacuum energy, a topic that captures the imagination of scientists and curious minds alike. At its core, vacuum energy is the energy that exists in empty space. It is not dependent on matter or radiation but is intrinsic to the vacuum itself. The concept comes from quantum mechanics, which describes the behavior of particles at the smallest scales. According to quantum theory, even in a vacuum where no particles are present, tiny fluctuations constantly occur. These fluctuations produce energy, giving rise to what is known as zero-point energy. Key principles of vacuum energy include the idea that space is never truly empty, that these energy fluctuations are unavoidable, and that they have measurable effects, even if subtle. Many people mistakenly think that empty space has zero energy, but vacuum energy shows that emptiness is never complete and still possesses a dynamic structure at the quantum level. The history of vacuum energy is intertwined with the development of quantum physics. The concept emerged in the early 20th century when scientists were exploring the strange behavior of particles at atomic and subatomic scales. One of the earliest mentions of zero-point energy came from Max Planck, who studied the energy of oscillators in 1911. Albert Einstein and Otto Stern contributed to understanding that even at absolute zero, some energy persists in systems. The Casimir effect, predicted by Hendrik Casimir in 1948, provided the first clear demonstration of vacuum energy through measurable forces between metal plates. The development of vacuum energy has involved numerous scientists over decades, including Niels Bohr, Paul Dirac, and Richard Feynman, each contributing insights into the quantum nature of space. Over time, this concept has evolved from abstract theory to a field with practical and observable implications, forming an essential part of modern physics. Vacuum energy operates through mechanisms rooted in quantum fluctuations. Even when a space is devoid of particles, the uncertainty principle ensures that energy cannot be completely zero. Particles and antiparticles spontaneously appear and disappear, a process that generates energy and contributes to the properties of the vacuum. The laws governing vacuum energy are grounded in quantum electrodynamics and field theory, which provide equations to calculate energy densities and predict measurable effects. For example, the Casimir effect is explained by considering the energy differences between allowed and restricted modes of quantum fluctuations between plates. The underlying principle is that the vacuum is not a passive emptiness but an active, fluctuating medium, where energy constantly emerges and vanishes, influencing matter and radiation around it. In the real world, vacuum energy manifests in subtle but observable ways. The Casimir effect is one of the clearest examples, where two metal plates placed very close to each other experience an attractive force due to changes in vacuum energy between them. Other everyday phenomena include the spontaneous emission of photons by atoms, influenced by the surrounding vacuum fluctuations. Vacuum energy also plays a role in the behavior of superconductors and quantum computers, where tiny quantum effects become significant. Experiments that detect these forces or energy fluctuations require precise equipment and controlled environments, yet they confirm that vacuum energy is not just theoretical but has observable consequences. Demonstrations of vacuum energy in laboratories provide a glimpse into the unseen forces at work in the universe, bridging theory with tangible evidence. The implications and applications of vacuum energy are both profound and practical. Technologically, vacuum energy influences the design of microelectromechanical systems and nanotechnology, where forces at very small scales are significant. It also plays a role in quantum computing, affecting the stability and behavior of qubits. Scientifically, vacuum energy is essential for understanding the cosmological constant, dark energy, and the expansion of the universe. Its influence extends to fields like astrophysics, where vacuum fluctuations can affect cosmic radiation and the formation of structures in space. By studying vacuum energy, scientists can explore connections between quantum mechanics and general relativity, offering insights that may lead to revolutionary discoveries about the universe's origin, evolution, and ultimate fate. Modern research into vacuum energy continues to uncover new insights and spark debate. Recent studies explore how vacuum energy might be harnessed or manipulated, though practical extraction remains speculative. Experiments with the Casimir effect, superconducting circuits, and quantum field simulations provide increasingly accurate measurements of vacuum fluctuations. Ongoing debates involve the exact contribution of vacuum energy to the cosmological constant and its role in the accelerating expansion of the universe. Future directions include exploring its potential in energy technology, understanding its impact on gravity and spacetime, and integrating it with other fundamental forces to develop a more complete theory of the universe. Scientists are keen to uncover whether vacuum energy can provide solutions to deep questions about energy conservation and the limits of physics. Despite its intriguing nature, vacuum energy presents significant challenges and paradoxes. Conceptually, it defies everyday intuition, since empty space seems to be nothing, yet it possesses energy. Contradictions arise when attempting to reconcile vacuum energy predictions with observations in cosmology, such as the so-called cosmological constant problem, where theoretical values vastly exceed measured ones. Open questions remain about how vacuum energy interacts with gravity, whether it can be controlled or exploited, and its implications for the origin of the universe. These puzzles highlight the limits of current knowledge and the need for continued research. They also demonstrate the philosophical depth of vacuum energy, as it challenges our understanding of existence, reality, and the meaning of emptiness itself. In summary, vacuum energy is the energy inherent in empty space, revealed through quantum fluctuations and measurable effects like the Casimir force. It emerged from the study of quantum mechanics and has evolved through contributions from many notable scientists over more than a century. Its fundamental mechanisms demonstrate that even the most seemingly empty regions of space are dynamic and filled with energy. Real-world examples and experiments confirm its presence and influence, while applications in technology and science show its practical importance. Modern research continues to explore its mysteries, raising debates and potential breakthroughs in physics and cosmology. Despite the challenges and paradoxes it presents, vacuum energy offers a profound window into the nature of the universe. By studying it, we not only gain insight into the behavior of matter and energy but also confront deeper philosophical questions about the essence of reality. Understanding vacuum energy enriches our appreciation of the cosmos and reminds us that what appears empty may hold vast and unseen forces, connecting the tiniest quantum fluctuations with the grandest cosmic phenomena. The study of vacuum energy encourages curiosity, scientific rigor, and philosophical reflection, showing that even in nothingness, there is something remarkable waiting to be discovered. The universe is filled with mysteries, some visible and others hidden deep within the fabric of reality. One of the most remarkable discoveries in modern physics is the Higgs boson. This particle is essential to our understanding of how matter acquires mass and why the universe behaves the way it does. Its discovery is a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. Today we will explore the Higgs boson, its principles, history, mechanisms, real-world implications, and the questions it continues to raise. At its core, the Higgs boson is a fundamental particle associated with the Higgs field. This field permeates all of space and interacts with other particles to give them mass. Without the Higgs field, particles would not have weight, and atoms could not form. Matter as we know it would not exist. The key principle behind this concept is symmetry breaking. In the early universe, forces and particles were indistinguishable. As the universe cooled, interactions with the Higgs field caused certain particles to gain mass while others remained massless. A common misconception is that the Higgs boson is the source of all mass. In reality, it only explains how elementary particles acquire mass. Mass from atomic nuclei, for example, comes largely from the strong force holding protons and neutrons together. The story of the Higgs boson begins in the 1960s. Theoretical physicists were struggling to explain why certain particles have mass while others do not. In 1964, Peter Higgs, along with several others including François Englert and Robert Brout, proposed a mechanism to explain mass generation through a universal field. This idea was initially controversial and faced skepticism because it could not be tested with the technology available at the time. Over the decades, advances in particle accelerators and detectors made it possible to search for the particle predicted by this theory. The discovery of the Higgs boson in 2012 at the Large Hadron Collider by the ATLAS and CMS collaborations marked the culmination of nearly 50 years of theoretical and experimental work. This timeline demonstrates the interplay between theory and experimentation in scientific progress. The Higgs boson operates through a simple yet profound mechanism. The Higgs field fills all of space like an invisible molasses. As particles move through this field, they interact with it, which slows them down and gives them mass. Some particles interact strongly with the field and become heavier, while others interact weakly and remain light. Mathematically, the behavior of the Higgs field is described by the Higgs potential and associated equations derived from quantum field theory. These equations follow the principles of gauge symmetry and spontaneous symmetry breaking. The underlying principle is that symmetry in nature can exist in a hidden form and can be broken to create diversity in the properties of particles. This mechanism explains not only why matter exists but also why the universe has structure and stability. The effects of the Higgs boson are subtle yet profound. While we do not encounter the particle in daily life, its influence is everywhere. The existence of mass allows planets, stars, and galaxies to form. Without it, matter would remain massless and diffuse, unable to clump together. Experimental verification has been achieved through high-energy collisions in particle accelerators, where traces of the Higgs boson can be detected from its decay products. These experiments demonstrate the predictive power of physics and our ability to probe phenomena far beyond human perception. Understanding the Higgs boson is not limited to theoretical interest, it provides insight into the very structure of the universe and why reality takes the form it does. The implications of the Higgs boson extend into both technology and science. In technology, particle physics research has driven innovations such as advanced detectors, superconducting magnets, and data processing techniques, many of which have applications beyond research laboratories. In science, the discovery of the Higgs boson confirms the Standard Model, the framework that explains particle interactions. This confirmation allows scientists to explore new questions, such as the nature of dark matter and the unification of forces. The impact on other fields, including cosmology, materials science, and quantum computing, is profound because understanding the basic building blocks of reality informs innovations across disciplines. Modern research continues to explore the Higgs boson in greater depth. Recent studies focus on measuring its properties with increasing precision, including how it interacts with other particles and whether it behaves exactly as predicted by the Standard Model. Ongoing debates concern whether the Higgs boson could be linked to new physics beyond the Standard Model, such as supersymmetry or extra dimensions. Future directions involve even more powerful accelerators, refined detection methods, and theoretical models that could uncover deeper layers of reality. Each discovery raises further questions, showing that science is a continuous journey rather than a final destination. Despite its elegance, the Higgs boson also presents conceptual challenges. The particle itself is extraordinarily difficult to detect because it is highly unstable and decays rapidly into other particles. Its mass appears fine-tuned, leading to theoretical puzzles known as the hierarchy problem. Some physicists wonder why the Higgs mass is not much larger, given the interactions that could affect it. Open questions include whether there are multiple Higgs bosons, how the Higgs field evolved in the early universe, and whether it connects to unknown forces or particles. These paradoxes demonstrate that understanding the Higgs boson fully remains one of the most profound challenges in modern physics. In summary, the Higgs boson represents a milestone in our understanding of the universe. It provides a mechanism for mass generation, explains the structure of matter, and confirms fundamental principles of particle physics. Its discovery required decades of theoretical insight, experimental ingenuity, and global collaboration. Beyond its immediate scientific significance, the Higgs boson opens doors to new technologies, deeper cosmological questions, and ongoing exploration of reality at its most fundamental level. The broader significance of the Higgs boson lies not just in its physical properties but in what it represents about human curiosity. It shows that with careful reasoning, imagination, and persistence, humanity can uncover the hidden workings of nature. Studying the Higgs boson reminds us that even the smallest particles can have enormous implications for the cosmos, and that understanding them can inspire new ways of thinking about the universe and our place within it. Reflecting on this discovery, one can see the philosophical dimension of science. The Higgs boson connects the abstract world of mathematical equations with the tangible reality of matter. It reminds us that the universe has rules, patterns, and structures that can be discovered and understood. By pursuing questions that may seem esoteric or abstract, scientists reveal truths that touch every aspect of existence. The journey from theory to observation illustrates the human capacity for insight, creativity, and perseverance, showing that the quest to understand the universe is an enduring and noble endeavor. The Higgs boson, though a microscopic particle, exemplifies the interconnectedness of knowledge, nature, and discovery. Its study bridges physics, technology, philosophy, and human curiosity. Each experiment, measurement, and calculation builds a more complete picture of reality, offering answers while raising new questions. In exploring the Higgs boson, we are not only learning about particles but also about the methods and principles that guide scientific inquiry. Its existence reinforces the idea that the universe, while complex, is intelligible and that the effort to understand it is both meaningful and transformative. Ultimately, the Higgs boson is a symbol of what science can achieve. It demonstrates the power of theoretical insight, experimental precision, and collaborative effort. It shows that human beings, through observation, reasoning, and innovation, can penetrate the veil of the unseen and bring hidden truths into light. As research continues, the Higgs boson will remain central to our understanding of the universe, inspiring new generations of scientists and thinkers to explore the mysteries of matter, energy, and the fundamental nature of existence itself.